బట్ సార్ ప్లీజ్ చెప్పండి 1:30 తర్వాత రమ్మని.
सर आपका ट्राई है सर, क्लास स्टार्ट्स at 9:05. हेलो. हेलो सर.
Good morning, students. Welcome back to the second day of electronic devices. So yesterday we have discussed what is the importance of this subject. Okay, why we need to study. We must understand. Okay, before doing anything, we must know why we are doing that. Okay, so that is the reason why we spent yesterday. Okay, on explaining the different terminology, different definitions, and what is the actual importance of the semiconductors and semiconductor devices is going to. Okay, and also we have given electrical systems, basically how we can classify them. Okay, and what is the where your semiconductor devices are going to play a role in that. And after that, basically we need to get the terminal characteristics. Any device that we are going to discuss, finally we need to get what? Terminal characteristics. And there are two types of signals that you are going to apply for the device. One is going to be what? DC signal, obviously. Okay, and another one is the AC. So DC VI characteristics or IV characteristics you have to obtain. And the second one is, in AC analysis, we know very well that there are two types of analysis. One is the transient analysis. The other one is what? Steady state analysis. Okay. So anyhow, in our discussion, unless it is mentioned, we are going to consider what? Steady state analysis. Please keep it in mind. And what is the other name for that? It is called as small signal analysis. What it is? Small signal analysis. Is it fine? Okay. And then we have given 4 important properties of the semiconductor material. Okay, starting with what are the different types of charges that are going to be present, nothing but polarity of charge carriers. So there are 2 types of charge carriers. One is the electron, negatively charged. Another one is what? Hole, which is positively charged. Okay. Then the second property is what? The electrical, conductivity is going to be decided by how many number of these charges are present. Nothing but what? Concentration of the charge carriers. Okay. Then the third one is how you are going to make these charges to move from one place to the other place. Nothing but we are calling it as what? Transport of charge. Okay. And the fourth one, how these are going to interact with the electromagnetic field. Okay. So that is what we have discussed. Okay. And here in the second property, we have very clearly seen that we can vary the carrier concentration 15 orders of magnitude in the semiconductor material. Whereas this is not possible practically in case of, metal or conductor and insulator. Okay. But in semiconductor, you can vary. Okay. So, sorry. So this is what we have discussed. Okay. Now, many of you are asking what textbooks. Okay. Yeah. Initially, I want to give a small suggestion here. Why I have not given initially the reference textbooks or other material is usually not only myself, any faculty, what they are going to do is they will collect the information from different sources. Okay. They will concise, and in a way they are going to present like, okay, whichever is going to be more simple for you. Okay. And here I'm not meaning that you don't refer the textbooks. Okay. But initially you get thorough with whatever we are teaching initially. Okay. Then you start practicing the questions, previous questions you can practice, and then you go for these textbooks. Once you get some understanding, then go for these books. Okay. These are the standard textbooks. Okay. But initially without, understanding, if you go and read the, any standard textbook, you may not be in a position to understand what they are telling. Okay. And that is the reason why I have not mentioned, but anyhow, I'm giving list of some, textbooks as well as other material also. In some textbooks, almost all the topics are covered, entire EDC, even analog. If you take the first textbook, integrated electronics, as well as electronic devices and circuits. Okay, these authors are the same, Millman and Halkias. These 2 textbooks, they are going to be very useful for EDC, that is electronic devices, circuits also, analog electronics also you can refer. Okay, digital also you can refer. Okay, but you may feel very difficult initially. You may not in a position to understand actually. Okay, so that is the reason why you get thorough with the things that what we are teaching. Okay, I'm sorry. And then you go and refer the textbooks. Okay. The third one, solid state electronic devices. The authors are Ben G. Streetman and Sanjay Kumar. This is also a very good book. Then electronic devices and circuit theory, Robert L. Boylsted and Nashel Sky. Then the fifth one, semiconductor physics and devices by basic principles by the Donald A. Neiman. Okay, there are other books also by this Donald A. Neiman where you can you have you can go for analog circuits also. Okay, then microelectronic circuits by Sedra and Smith. This is also very good book. Okay, yeah, here this also you can have understanding of analog electronics also presented in this book. Very good book. Okay, then 7 fundamentals of microelectronics by Rajavi. Then digital integrated circuits, a design perspective, Rabe and Chandrasekharan. Okay, then another one, CMOS VLS design. Basically 7, 8, 9 you can go for MOSFET, even microelectronics. Sixth one is also you can refer the MOSFET. Okay, MOSFET and CMOS. Okay, hope I am clear. And anyhow, each topic I'll give which textbooks you can refer. Okay, and the 10th one I've given an NPTEL course here actually. Okay, which is named as solid state devices. The course instructor is going to be S. Karmalkar, Dr. S. Karmalkar of. This course will be around you have 42 lectures. Okay, maybe around I think around 20 lectures are only dedicated to the semiconductor theory. Okay, so initially if you go and listen, you may not in a position to understand this. Okay, but anyhow, most of the semiconductor theory that I am going to teach here, okay, most of it is going to be extracted from this NPTEL course. Okay, I have refined, or I can say customized to our requirement. Okay, there are so many things that are taught by this Professor S. Karmalkar. Okay, but I have concised, okay, or customized to our requirement. Okay, and particularly the semiconductor theory, you can refer anyhow first 2 textbooks also you can refer. I'm talking about the semiconductor theory now. Okay, anyhow later on I'll give, whenever I start the new topic, what are the reference textbooks. Okay, and you can refer this also, Sanjay Kumar. Okay, and this. Okay, these 4 you can refer for the semiconductor theory. Okay, very good. Okay, yeah, again one thing. Okay, the notation, suppose if I take some parameter, how we are representing is called as the notation. So this notation may change from textbook to textbook. Please keep it in mind. Notations, definitely they will change from person to person, textbook to textbook. But finally, what is important is you have to understand the concept. The definitions and the concept, if you understand, notations, okay, will not matter for you. Okay, but most of the times we are bothered about the notations rather than the concept. Suppose you take voltage between 2 points, V12, you may see in some textbooks it is V1 minus V2. In some textbooks it is V2 minus V1. Both are correct. The reason is, the important point is how you are defining V12 is important here. Whether you are saying V12 as voltage at 0.1 with respect to 2 or voltage with reference to 0.1 at 2, both are different. That's why you are getting V1 minus V2 in some textbooks. In some textbooks it is V2 minus V1. Okay, so hope I am clear. Okay, because we may have different notations. Okay, from textbook to textbook it is going to vary, but what you have to understand is what concept. If you understand the concept, you can easily get adapted to these notations. Okay, yes, so hope I'm clear with whatever. Okay, so again my sincere advice, please get thorough with whatever I'm teaching here first. Okay, practice and then go and refer the textbooks. Okay, yes. And one more request from my side, when I'm teaching here, okay, so please don't sit ideally, okay, just listening to the lecture is not enough. Please try to take down the notes. It is very important for you, okay. You may not feel now, but it's going to be very, very important, okay, because now we are facing the challenge, you know, this coronavirus has made everyone, okay, to realize what is the importance of life. There are you know, we are running behind many things, but now we are sticking only to the life, okay. So we have to, you know, accept the things, okay. But even when you are sitting in the physical class, many times you may physically present in the class, but mentally you will be out of the class many times, no. And now it is not the control environment. At least the physical class is the control environment where teacher is there at least, okay. But here it is not the controlled environment. You have to control yourself. There is no other way. You have to dedicate, or you have to, when it is 9 to 1 class, you should be there at 9 o'clock start sharp, and up to the end of the session you have to stay. You have to ensure that by yourself you are staying there, okay. So nobody else can control you, okay. Yeah. And one more request, from tomorrow onwards we'll try to not try to sharp 9 o'clock we are going to start. So please come to the, you know, log in your IDs before, you know, at least 5 to 10 minutes, so that we can start the session by sharp 9 o'clock, okay. Yeah. Now, so I have given the syllabus, and what is the starting topic that we need to consider is the semiconductor theory, okay. So we need to start with semiconductor theory, okay. And for our convenience, we have divided this into 4 parts, okay, starting with equilibrium concentration, equilibrium, carrier concentration, okay. And after this we'll discuss about carrier transport, okay. And the next one is what? Excess carriers that we are going to consider, excess carriers. And finally, procedure for device analysis, procedure for device analysis, okay. So this is what in the semiconductor theory we are going to consider, okay. Now again, equilibrium carrier concentration, we'll make it into, we'll start with some basic concept, okay, basic concepts, and we'll try to discuss about intrinsic semiconductor, okay, and extrinsic semiconductor, okay. So these are the things that we are going to consider, okay, starting with basic concepts, then we'll go for intrinsic semiconductor and extrinsic semiconductor, okay. Yeah, here if you understand intrinsic semiconductor concepts with little modifications, we can easily understand extrinsic semiconductor material. Please keep it in mind, okay. Now in basic, you know, concepts, we'll try to understand, okay. So let me write it in the next page. So we are considering initially what? Equilibrium carrier concentration, okay. So this is the starting topic, equilibrium carrier concentration, okay. So in this one, yeah, I'm giving this for your convenience, okay, for your understanding purpose. Okay, so what we are going to start with, basic concepts. Okay, anyhow, these basic concepts you know already, and I'll just refresh these things. Okay, but it is very important. Okay, see, whatever, again I'm repeating this point, whatever I'm teaching, this is required for you, please keep it in mind. Okay, then we'll discuss about intrinsic semiconductor, and finally what, extrinsic semiconductor. Extrinsic semiconductor. Okay, now if you consider basic concepts, okay, so what we are going to consider is the first one which we must understand is types of semiconductors. What it is? Types of semiconductors. Okay, and the next one is, many times we are going to use a word or term called as equilibrium. This we must understand what it is. Okay, and also we use many times this term called as, you know, steady state. Okay, so both are different. Equilibrium is different, steady state is different, but we are going to use many times these two terms, but maybe without understanding we are using. Okay, and we'll try to understand what is called as wave particle duality. Wave particle duality. So this is what we are going to discuss in basic concepts. Okay, now this intrinsic semiconductor as well as extrinsic semiconductor, okay, we can have two models to understand this characteristics. Okay, one is called bond model. Okay, bond, because there is a covalent bonds that are going to be present, so that is called as what, bond model. Another one is band model, okay, or energy band model. Okay, so we have to develop an energy band diagram. From that we can give the important characteristics. Okay, so here in intrinsic, whatever we are considering now, bond model and band model with little variation, again we are going to discuss in extrinsic semiconductor. Okay, so it is bond model and band model. Hope I am clear. So if you understand bond model of intrinsic with little variation, we can easily get extrinsic semiconductor bond model. Okay, and if you understand the band model or energy band model of intrinsic semiconductor, we extrinsic semiconductor band model. So one is going to be qualitative analysis, another one is going to be quantitative. Bond model will give qualitative analysis, that is how the things are going to be. Then band model is going to be the quantitative analysis, means mathematical equations and all we are going to derive. Okay, so this is about the first topic that we are going to consider. What it is? Equilibrium, carrier concentration. Okay, now let us start the basic concepts. Okay, so in that, what we need to consider first? Types of semiconductors. Okay, so hope I am clear with whatever I am explaining. Okay, yeah, let us start with basic concepts. Basic concepts. Okay, so in that we are considering what? First one is types of semiconductors. Okay, what it is? Types of semiconductors. Yeah, you know already, but we'll see what is the difference, what you know and what actually you need to understand. Okay, now let us consider. If I suppose this is the semiconductor. Okay, so one way of classifying this is I can have a pure semiconductor. Okay, so please try to understand pure. I can have intrinsic and another possibility is extrinsic. Okay, yeah, we'll define how they are going to be, we'll define it. And another way of classifying the same is we can call it as simple, or we also call it as elemental. Okay, simple or elemental semiconductor. And another one is what? Compound semiconductors. Hope I am clear. Another way of classifying it is what? Compound, simple and compound. Okay, hope I am clear. Okay, so now what are the examples that you can give for simple or elemental? Is nothing but germanium, silicon. What about compound? The name itself is giving, it's the combination of third group and fifth group elements. Okay, so the very good example for this, gallium arsenide, gallium arsenic phosphide, like that. We can have 2, 3, even 4 also, combination of 4 elements. Okay, so this is one way is simple, elemental, another one is what? Compound. Okay, hope I am clear. Yes. Now come to the how we can define, pure semiconductor. The name itself is giving, pure means there are no defects, okay, or I can say no impurities. Hope I am clear. Pure means what? There are no defects or there are no impurities. Then you can call it as what? Pure semiconductor. Okay. Now, if you remember, I think we might have defined intrinsic as what? Pure semiconductor. But there is a difference between pure and intrinsic. There is a difference. Okay. So what is the difference is, in intrinsic semiconductor material may not be a pure semiconductor. There can be some defects and impurities. Okay, impurities and defects may be present, but the condition is the number of electrons and holes that are present in intrinsic semiconductor must be same as in case of pure semiconductor material. I'll repeat this point, please concentrate. In semiconductor material, there are 2 types of charge carriers. What are they? Electrons and holes. Yes. Now, I'm sorry. In case of pure semiconductor material, okay, there will be some electrons and holes. And anyhow, we have very clearly defined there should not be any impurities, or I can say there are no defects in case of pure semiconductor material. Now coming to the intrinsic, there can be some impurities and defects that can be present, but what is the condition? The number of electrons and holes that are present in intrinsic semiconductor material must be same as that of in the what? Pure semiconductor. So since there are defects and impurities, okay, so one impurity has to compensate the other, then only this is possible. Okay, yes or no? Okay, so let me write that point. What we are considering now, we are defining the intrinsic. So how we can define this? The intrinsic semiconductor, there can be some defects, okay, and impurities. Defects and impurities, but what is the condition? The number of electrons and holes must be same as that of pure semiconductor. Okay, pure semiconductor. Hope I am clear. Yes. Okay, please try to take down the notes. Please don't sit ideally and listening. Okay, so please take down the notes. Okay, I'm going very slow, so you can take it down. Okay, am I clear? So holes, number of electrons and number of holes are going to be same as that of in the pure semiconductor, but there can be some defects and impurities that can present. Okay, so now this is possible. This is possible only when one impurity compensates the other impurity. Okay, then only it is possible, yes or no? Because if there are impurities, definitely there will be effect on the carrier concentration. But the condition that we have given here is what? The number of electrons and holes that are present in the intrinsic semiconductor material must be same as that of in the pure semiconductor. But what is the difference? Here there are no defects and impurities in case of pure semiconductor. But what about intrinsic? Defects and impurities can be there, but the number of electrons and holes, okay, number of electrons and holes must be same as that of pure semiconductor. Okay, hope I am clear. Okay, so 1 minute. Okay, so hope I am clear with the types of semiconductor materials. Okay, so anyhow, this simple and elemental we are going to consider later. Okay, but again, if you consider the semiconductor, okay, so the simple and elemental we have given, no, simple or elemental, and another one is compound. Okay, simple or elemental, and another one is what? Compound. Okay, so this simple or elemental we also call it as, this is also called as indirect band gap. Anyhow, these things we are going to discuss in detail later. For time being, you remember indirect band gap. Okay, and this compound is called as direct band gap semiconductors. Okay, now this again, this simple elemental, you can have pure, intrinsic, extrinsic. Okay, yes or no? This is possible, pure, intrinsic, extrinsic. Again, compound also you can have pure, intrinsic, extrinsic. Okay, yes. Now in the previous one, how you can define this extrinsic? Sorry, see, extrinsic means you are adding the impurities. Yes or no? Definitely there will be impurities. By using the process called as doping, either you are introducing the third group element, which results in p-type semiconductor. Yes or no? P-type. And if you are doping with the fifth group element, which results in n-type semiconductor. So definitely there will be impurities that are going to be present, obviously. Okay. Yes or no? Okay. So this is about what types of semiconductors. So again, simple and compound, you can have, simple can be again, it nature can be pure, intrinsic, extrinsic. Similarly, what about compound? It can be pure, intrinsic and extrinsic. So hope I am clear with what I have written now. Okay. So this is about what? Types of semiconductors. Okay. Now let us move to the next one. What it is? To the next one, we need to understand what is meant by equilibrium. Okay, we need to understand what is equilibrium. Okay, so this also called as, we can call it as thermal equilibrium. What it is? Thermal equilibrium. Okay, it is default. even though if I say equilibrium, default, what is the parameter that is going to be present? Thermal temperature. So that's why we are calling it as what? Thermal equilibrium, or it is also called as thermodynamic equilibrium. Thermodynamic equilibrium. Okay, but simply we'll call it as what? Yes, we'll simply call it as equilibrium. Okay, now we'll try to understand this point. Okay, so please concentrate. Now let us consider this is the semiconductor material. Okay, let us consider this is a semiconductor. Okay, so this is the semiconductor. Okay, and surrounding this, what I have? Environment. Yes, sir. Surrounding this, I have environment. Now, so how I can say the semiconductor is in equilibrium with its environment? Obviously, it should be with environment default. Okay. So how we can say is, please try to understand. I will define. Okay, and then I'll also write it. Please concentrate. First listen, then you can take the notes also. Okay. Now, for every process, the semiconductor is said to be in equilibrium with its environment if for every process that is going on between semiconductor and environment. I'll repeat, for every process that is going on between semiconductor and environment, there is an inverse process. Okay, not only that, at the same rate. Okay, that is an inverse process also at the same rate. Okay, so yeah, first I'll write the definition and try to explain. Okay, so how you are defining this? The semiconductor is in equilibrium with its environment. Okay, with its if for every process that is going on between semiconductor, okay, between semiconductor and environment, and sorry, and environment, there is an inverse process, and not only that, at the same rate. Okay, at the same rate, then you can say it is under equilibrium condition. Now, not only with environment, it is also applicable. It is also applicable for the processes within the semiconductor. Yeah, we'll try to understand. Okay, within the semiconductor. Is it fine? Again, I'm repeating this. If I want to say the semiconductor is in equilibrium with its environment, for every process that is going on between semiconductor and environment, there exists an inverse process at the same rate, and this is also applicable for the processes within the semiconductor. Okay, we'll try to understand what this. Okay, now for example, let us consider 10 electrons are moving from semiconductor to environment. Okay, some example I am taking. Okay, 10 electrons are moving from semiconductor to environment. So what is the inverse process? Same 10 electrons has to be moving from environment to semiconductor material. Not only that, what we have given at the same rate, this is also important. One is the inverse process. Okay, one is the inverse process and another one is what? At the same rate. What is the meaning of this? Suppose 10 electrons, okay, 10 electrons per second if you consider, same 10 electrons has to move from environment to semiconductor within 1 second. Hope I am clear? Within 1 second, 10 electrons are moving from semiconductor to environment. Same, okay, same number, 10 number of electrons should move from environment to semiconductor. And this is also applicable within the where? Semiconductor also. Suppose at two different points you consider, then this has to be happening within the semiconductor also, not only with the environment. It has to happen within the within the semiconductor. Hope I am clear? Yes? Okay. Then you can say it is under equilibrium condition. Okay. Now, the other name that is given for this, it is also called as, okay, it is also called as principle of detailed balance. What it is? It is called as principle of detailed balance. We'll see what is the meaning of this. See, here we have taken 10 electrons now from semiconductor to environment. Okay, again for your understanding purpose, I am taking an example and explaining this. Suppose out of 10 electrons, okay, 10 electrons, let us consider 3 electrons, okay, 3 electrons are having a mass of m1, okay, m1, and another 3 electrons have mass of m2, okay, and what about remaining? Let us take 4 have mass of m3, okay, 4 electrons, okay, 4 electrons have mass of m3. Am I clear? 3 electrons having the mass of m1, another 3 electrons have mass of m2, and the remaining 4 electrons have mass of m3. So they are moving from semiconductor to environment. Now when the reverse process is happening or inverse process is happening at the same rate, okay, 3 electrons should have the mass of m1, another 3 electrons should have mass of m2, and the remaining 4 electrons has the mass of m3. In that detail you have to consider. Even if you consider the mobility and all also, it's the same. So that is the reason why we'll call it as what? Principle of detailed balance. Okay, hope I am clear. The reason why we are calling it as principle of detailed, in that micro level you have to observe the particles. Okay, anyhow, here if you understand the definition of the equilibrium, it is well and good. Fine. Okay, so please try to spend some time on your own to understand this definition that I've given. Okay, am I clear? Okay, now how to check whether the semiconductor is in equilibrium or not? We'll see that. Okay. Okay, now the semiconductor is in equilibrium, is in if you have to check two conditions here. Okay, we'll see what they are going to be. The first one is, okay, if there is no external excitation, there is no external excitation, okay, other than temperature, this is the first condition that you have to verify. What is that? There is no external excitation, but default there will be a temperature, obviously. Okay, so other than temperature, this is one. Then the second condition that has to be satisfied is there is no net transfer of energy or charge. Okay, there is no net transfer of energy or charge. So these two conditions has to satisfy if I want to say the semiconductor is in equilibrium condition. Okay, yes, hope I am clear. Now let us take some examples and verify whether it is the equilibrium condition or non-equilibrium condition. Okay, now let us consider this is the semiconductor. Okay, this is what? Semiconductor. Okay, now let us consider this is temperature T1, this is T1, T2, and let us take T2 greater than T1 or T2 less than T1, it's your wish. Okay, I'm taking T2 greater than T1. Please tell me whether this is in equilibrium or not. Try to understand in your own. You check these two conditions. Spend 1 minute of time to answer this question, please. This is the semiconductor I am taking. So this temperature is T1, this temperature is T2, and T2 is greater than T1. Please try to answer this question on your own. I'll explain anyhow. Spend 30 seconds or 1 minute. Yeah. Is it in equilibrium? Yes. Yeah. How to check it? You have to check these two conditions. Is the condition 1 is satisfied here? Condition 1. What is the condition 1? There should not be any external excitation other than the temperature. Yeah, that is satisfied here because there is no any external excitation that we are applying. But anyhow, temperature is there. It can be. Yes. So condition 1 has been satisfied. Then what about condition 2? Condition 2 is what? There should not be any net transfer of energy or charge. Am I correct? So is there any net transfer of charge or energy here? Obviously, your temperature difference is present. T2 greater than T1, definitely there is an energy transfer. You know very well this. Yes or no? T2 is greater than T1 or other than your T1, definitely there will be transfer of energy. So condition 2 is not satisfied. So what you can conclude? This is non-equilibrium condition. This is under non-equilibrium condition. Hope I am clear? Yes. Now let us take another example. Again, I am taking a semiconductor. Okay, I'm taking a semiconductor. Now, I'll illuminate this semiconductor material. Okay, I'm making the light energy to fall on this with the photon energy of h nu, which is greater than or equal to energy gap. Yes. Okay. Now tell me whether this is under equilibrium condition or non-equilibrium condition. Again, check the condition 1 here. Check the condition 1. What is it? There should not be any external excitation, but you are applying the light energy here. So condition 1 itself failed here. I'm sorry. Condition 1 itself is failed. So straight away you can say it is under non-equilibrium condition. Anyhow, we'll check for the condition 2 also. Now, what will happen when you make the light energy to fall? What will happen? the light energy is absorbed on the surface of the material, then electron hole pairs are going to be generated. So you can have, suppose if I consider electron concentration on the surface, it will be more than the electron concentration in the inside. Yes or no? Inside volume if you consider. So there is a concentration gradient which leads to movement of carriers. Hope I am clear. I'll repeat this point. The light energy which you are applying will be absorbed by the material on the surface, okay, and it is generating electron hole pairs on the surface, okay. Then if you consider, okay, so on the surface there are generation of electron hole pairs. So definitely there is a concentration gradient and carriers will move from higher concentration to lower concentration. So condition 2 is also failed. So straight away I can say it is non-equilibrium condition. This is also what? Non-equilibrium. Yes. Let us take another example. Semiconductor. Okay. Now I am applying an external voltage here, which is V. Yes. Okay. Now what will happen? There is an electric field that is going to be developed. Okay. Because this is plus and this is minus. There is an electric field. Okay. Which results in a current of I. And straight away you can check whether condition 1 is satisfied. No, because you are applying the external voltage here. What about condition 2? This is also not satisfied, because definitely there is a movement of carriers because of the applied potential or electric field. So this is also what? Non-equilibrium. Hope I am clear. This is also non-equilibrium. Okay. Yes. So this is how you can check the material or device is in equilibrium condition or not. Two conditions. There should not be any external excitation other than the temperature. What about second? There is no net transfer of charge or energy. Both has to satisfy. Okay. So please again try to understand this point. Is it fine? Now try to answer my question. Whether your electronic device, any semiconductor device that you are going to consider, whether you need to, if you want to get anything out or you want to use it, whether it is in equilibrium or non-equilibrium condition. If I want to use your semiconductor device for some application, whether it should be under equilibrium condition or not. Obviously, it should not be under equilibrium condition. Yes or no? If it is under equilibrium, what you are going to get? Nothing that you are going to get. Okay. So please find what it is. If I want to use the semiconductor for any application, okay, semiconductor device for any application, you have to disturb its equilibrium condition. Okay, so that point I am writing here. Semiconductor devices, are only useful under non-equilibrium conditions. Non-equilibrium conditions. Okay, we cannot get anything out of a device which is in equilibrium. Please try to understand this point. Okay, you have to disturb the equilibrium condition of the device. Then only we can use it. Suppose you take the diode, for example, either you have to apply the forward voltage or reverse voltage. Okay, yes sir. Under equilibrium, what you are going to get? Nothing. Fine. Okay, but the device analysis, you must start with the equilibrium, so that it's going to be easy for other bias conditions. Okay, anyhow, that we are going to discuss later. Is this point clear? Semiconductor devices are only useful under non-equilibrium conditions, and we are not able to get anything out of the device which is under equilibrium condition. Okay, now many practical situations, yeah, please, whatever the points that I'm giving here, I'm not giving just like that. Okay, again we are going to consider these points when we are going to discuss the devices. Please keep, I'm giving here, again we are going to refer back, and that is the reason why I'm giving, step by step I am writing. I am allowing you to take the notes also. Please take the notes. Okay, so many practical situations for semiconductor devices, okay, can be considered, okay, or can be treated as quasi-equilibrium situation. I'll see, we'll explain what is that quasi. Okay, many practical situations for semiconductor devices can be considered as what? Quasi-equilibrium situations. Okay, so what is that we are giving here? Quasi-equilibrium. Okay, so here the word quasi represents small deviation. What it is? Small deviation. Quasi represents what? Small deviation. So quasi equilibrium means what? Small deviation from the equilibrium condition. So please, again, when you suppose take the PN junction, we'll start the analysis of the PN junction with the equilibrium or open circuit condition, okay, or zero bias condition. We are going to obtain many parameters. Once we know the analysis or the parameters of the equilibrium condition of the device, from that, suppose you are applying the forward bias, and it will be a small deviation from equilibrium condition. So whatever the analysis that we have done for the under the equilibrium condition, with little modifications we can extend for what? Bias condition also. And that, okay, so the first point is what? Semiconductor devices are not going to be useful under equilibrium condition. You have to disturb its equilibrium condition, then only you can get something out of the device. And what about the second point? Many practical situations in the semiconductor devices can be considered as what? Quasi-equilibrium conditions or situations. What is meant by sorry, quasi? What is meant by quasi? There is a small deviation. Okay, so please keep it in mind. Whatever we are defining here, they are going to be useful for us. Okay, hope I am clear with. Now we have done with the term called as equilibrium. Let us go for steady state. We are considering now what? Steady state. Yeah, please try to concentrate. Okay, initially you may feel bored also, but if you don't understand this terminology, okay, because we are going to use these terms many times. Okay, I think you have used it, but without understanding we are using. So we must understand what it is. If you understand what that condition is, we can easily get the other parameters. Okay, and that is what I am trying to do. Okay, so please pay attention. Okay, steady state. So we have done with the equilibrium. We'll try to define what is steady state. Yeah, you know very well what is meant by steady state. Mathematically, what we will do? Steady state means dou by dou t equal to 0. No, that is, there is no process that is our variable that is going to change with respect to time. As simple as that. Am I correct? Okay, so let me write that. All processes, what it is, all processes are constant, okay, with respect to time or as a function of time. All processes are constant as a function of time. Hope I am clear. But here there is no condition that, okay, I'll write in brackets, there is no condition that there should be an inverse process. Here there is no condition. But what about equilibrium? It is must. Okay, so right, not necessary, it is not necessary that, okay, necessary that for every process, there should be an inverse process. Okay, every process there should be an inverse process. Hope I am clear. It is not necessary that, okay, it is not necessary, okay, that for every process there should be an inverse process. But what is the condition? All processes are constant as a function of time. Okay, mathematically what we will do actually, dou by dou t or d by dt equal to 0. That is what we are going to put. Okay, hope I am clear. Now we can give the relation between equilibrium and steady state now. Okay, now let me draw this. Let us take, this is one circle, okay, and this is another one. Okay, so again try to spend some time here. Okay, here one circle is going to represent equilibrium, the other one is going to represent steady state. That is, one can be a subset of the other actually. Okay, am I clear? Please take around 30 seconds to 1 minute, try to answer out of this red and blue circle now, which one is going to be equilibrium and which one is going to be steady state. So try to identify. That is, one is going to be the subset of the other. Try to identify with the definition. Yes. So what about this blue circle? What about this blue circle? It's going to be equilibrium. And what about this one? Is the steady state. Okay, steady state. Yes, try to spend some time here. So what is the meaning of this? Okay, so let me write first what is the physical meaning, and then I'll try to explain it. Okay, so if a semiconductor okay is in steady state, okay, please try to concentrate. If a semiconductor is in steady state, it need not necessarily, okay, need not necessarily be under equilibrium. Please try to concentrate. If I say the semiconductor is in steady state condition, it need not necessarily be under equilibrium. It may or may not be. Okay, but in the other way, suppose if I say the semiconductor is in equilibrium, but if the semiconductor the semiconductor is in equilibrium, okay, then it is under steady state. Yes or no? It is under steady state. So it is definitely under steady state. Definitely under steady state. Please try to understand this. Okay, so if I say the semiconductor is in steady, may or may not be in the equilibrium condition, but if I say the semiconductor is in equilibrium, then definitely it is under steady state condition. Okay, we can very simply understand this one. The condition, you can see this condition is not required in case of steady state, but what about equilibrium? This condition has to satisfy. It is the necessary condition. It has to satisfy, but it is not necessary. Okay, now this portion, this entire thing is what? Steady state actually. Whatever the area that is present under a red circle, you can consider as the steady state, no? So that is equilibrium is included here. Okay, but this part out of you exclude this area within the blue circle, what it is going to represent? It is still in steady state. Yes or no? This is still in steady state, but not equilibrium condition. What about this? This is equilibrium as well as steady state. Area within the blue circle, what it is going to represent? It is steady state as well as equilibrium. But what about the area excluding this, excluding the area in blue circle? It is steady state but not in the equilibrium condition, and that is what we have given here. So if a semiconductor is in steady state, it may or may not be in equilibrium, but if the semiconductor is in equilibrium, definitely it is under steady state condition. Hope I am clear with what I have given. Yes. Okay. Now, usually, if you consider the transient conditions, what is transient condition? Okay. If you take the transient condition, this can be approximately taken as what? This is steady state, so it is quasi steady state or quasi static state. Okay, so this can be approximately taken as what? Quasi steady state, or it is called as what? Quasi static. Okay, so please try to understand this. Transient conditions you know very well. So that can be taken as what? That can be taken as what? Quasi steady state or quasi static state. Okay, that is nothing but what? If you derive the conditions under static condition or steady state condition with little modifications, you can apply for the transient. Like in the previous case we have given what it is? Whatever we are deriving under equilibrium condition, with little modifications we can extend to the quasi equilibrium. Again, what is quasi here? There is a small deviation. Okay. Hope I am clear. Yes. Is it fine now? So three topics that what we have considered is over. Okay. So starting with types of semiconductors, then we have discussed about equilibrium condition, or what is the other name for that? Thermal equilibrium or thermodynamic equilibrium. Okay, and the other one is what? Steady state. Okay, yeah, please try to spend some time here to understand the definitions of equilibrium and steady state, and how you can represent this one specifically. Okay, this one. Okay, so based on this is the graphical representation. The same thing I have given in the words. Okay, same thing I have given in the words. If you know this, you can get this. If you understand this one, you can write this. Okay, that is how you have to understand the subject. If I know the definition, okay, in words. From that you must able to write the mathematical equation. From the mathematical equation you should able to write the, in words or statement form. You should have that. Okay, fine. Yeah, now another anyhow, this you might have studied even maybe in your +1 +2. Okay, I'm just refreshing. Later on these things we are going to use, and that is the reason why I'm spending time here. Okay, we'll take what? Wave duality. Okay, what is that? Wave particle duality. So what is this wave particle duality? Yes, what is the wave particle duality? So the energy or the matter is going to propagate in the form of streams of particles or as a traveling wave. We know very well this point. Yes or no? Yes. Okay, let me write that. The energy, the energy or matter propagates, okay, energy or matter propagates in the form of streams of particles, streams of particles are, so what is other nature? It can be a wave or it can be a particle. So this is particle we have given. What is other nature? Traveling wave. Wave is nothing but traveling wave here. Okay, streams of particles are traveling waves. Okay, yes. Now we'll try to give a tabular column here. Okay, so that you can you can understand. Yeah, anyhow, this you know already. Again, I'm just for your refreshing purpose, I'm doing this. Okay, let us take a tabular column. Please, you can draw simultaneously. Okay, so what we are going to consider is particle stream here. Yeah, please, this one we are going to use. Okay, that's why I'm giving it. Okay, don't consider it is not required. Okay, please take it down. Okay, particle stream. So starting with photon, we'll see what these are going to be. Photon, okay, then electron we'll consider, and another one is called phonon. Okay, and we need to understand what is the wave nature. Okay, what is the variable that is going to change with distance and time. Okay, and what is the wave equation that we are going to consider. Okay, so this is traveling wave, variable with respect to distance and time, and finally the wave equation that we are going to consider. Yeah, please take it simultaneously. Okay, so in this one what we are going to consider, what is the corresponding traveling wave, okay, then variable with distance, okay, and time. Here I am writing x and t, one dimensional I am taking here. Okay, or if you want to write x comma y comma z, you can write, that is 3 dimensional. Okay, basically what it is, variable with respect to distance and time. Okay, and finally name of the wave equation, name of the okay. So the particle streams are going to be, one is the photon, another one is electron, phonon, and correspondingly we should give what is the traveling wave, what is the variable with respect to distance, and what is the name wave equation name that we are going to give. Yeah, what is the wave nature of a photon? I think you know very well. Please, what is the traveling wave? It is nothing but the electromagnetic wave, EM wave. Okay, what it is? Magnetic, or I can say simply EM wave. I'll write. It is nothing but what? EM wave. Yeah, for an electromagnetic wave, which parameters are going to vary with respect to distance and time? Obviously, the electric field and the magnetic field. Am I correct? What are the variables or parameters that are going to vary with respect to distance and time in an electromagnetic wave? Nothing but electric and magnetic fields. And what about name of the wave equation? How you are going to describe? Maxwell's equations. Okay, Maxwell's equations. Hope I am clear. Yes. Now come to the electron. What is the corresponding wave for an particle nature is electron? What is the traveling wave? It is de Broglie. Yeah, here I think you might have studied already these things. Okay, I'm just giving glimpse of that. Okay, because from this we need to extract what we require immediately after this discussion. We'll start with the intrinsic. We need to take it. Okay, and that is the reason why I'm giving. Okay, now what is the variable with respect to distance here? It's going to be the probability. Okay, yeah, to understand some of the concept, you may require some concepts from the chemistry and physics of your +1, +2, even high school. Okay, so wherever it is required, I'm extracting from that. Okay, if you have any doubt, please go back and refer. There is nothing wrong. Please go back and refer. Okay, because whatever I require, I'm taking here. Okay, I cannot cover all those things again. Okay, hope I am clear. Okay, now what is the wave equation here? It is the Schrodinger's wave equation. Okay, it is the Schrodinger's wave equation. Okay, now anyhow, this phonon may be a new thing for you. Phonon is nothing but a vibrating atom. You can call it as phonon. What it is? A vibrating atom. Vibrating atom is called as what? Phonon. So how and what are the characteristics? We'll see within maybe 10 minutes. We are going to consider it. Okay, is it clear? Phonon is what? Vibrating atom. Now what is this is the particle nature. Phonon is the particle nature. What is the traveling wave? It is going to be called as elastic wave. Yeah, please, you need to understand and remember the corresponding particle and wave nature here. Okay, for photon it is EM wave, electron is the particle nature, de Broglie's wave is the traveling wave. For phonon is the particle, and what is the wave nature? It is elastic. Okay, and anyhow we called it as what? Vibrating atom. No, so what is the variable with respect to x and t? Is the displacement. What it is? Displacement. And here there is no single equation that, okay, with a, there are many equations that we can represent. Okay, and that is why I'm putting dash. It means what? There is no single equation. Yeah, please try to understand the difference. Okay, I'm not writing that there are no equation. What is that? No single equation. There are many equations that can be considered here. Okay, yeah, anyhow whatever you require, I'm giving it. Okay, you just think about that. If you want further, you can go and refer the corresponding books. Okay, hope I am clear. So this is what the particle nature and the wave nature I'm giving here. Okay, and correspondingly what are the variables that are going to be vary with respect to distance and time, and what is the name of the wave equation. So photon, what is its corresponding wave nature? EM wave. What are the variables in an electromagnetic wave with respect to distance and time? Electric and magnetic field. How you are describing, or what is the wave equation? Maxwell's equation. Okay, there are four. Call any electromagnetic field as the electromagnetic field. Okay, 4 Maxwell's equation along with one continuity equation, current continuity equation. These are the 5 that has to be satisfied. Okay, yeah. I'm not going to further discuss that. Okay, now electron. What is the corresponding wave? De Broglie's wave. And what is the variable with respect to distance and time? It is probability. And it is the Schrodinger's wave equation. Phonon is the particle nature. What is its corresponding wave nature? Elastic wave. And what is the variable with respect to distance and time? It is. And there is no single equation that can be represented here. Please again, this it doesn't mean that there are no equations. There are multiple equations that are going to be present. Okay. Now, one important relation that we are going to derive here, okay, is this E is equal to, it is the energy of the photon, E is equal to h nu. Okay, E is equal to what? H nu. This is energy. Okay, and what is H? Planck's constant. Nu is the frequency. Okay, hope I am clear. And another one is going to be the momentum, P. Okay, I am representing with small p. What is this? Momentum. This is energy and this is momentum. Okay, so this P is going to be H divided by lambda. Again, this is the Planck's constant, and what is this lambda? Is the wavelength. I am clear? E is equal to what? H nu. P is equal to H by lambda. What is E here? Energy. This is momentum. Okay, so let me write that. This is energy. And what about this? Momentum. Okay. And what about this nu? This is frequency. Okay. And what about lambda here? Wavelength. And what about H? Planck's constant. Okay. So here, this E and P represents what? E and P. Which nature it is going to represent? Please try to understand. Because we have given energy or matter can propagate in the form of streams of particles, or it can be traveling waves. Now there are 4 parameters. No, anyhow, H is a constant. Okay. So there are 4 parameters. What are they? Energy, momentum, frequency, wavelength. Now out of these 4, which are going to represent the wave nature? Yes. So energy and momentum obviously represents what? The particle nature. Am I correct? Okay. So E and P represents properties of what? Properties of what? Particles in the stream. Properties of particles in the stream. Okay, please try to understand. Okay, and what about other 2 parameters, that is frequency and the wavelength. Nu and lambda represents what? Properties of the wave, traveling wave that is associated with the streams of particles. Okay, so represents properties of traveling wave, properties of traveling wave associated with the what? With the streams of particles. The streams of particles. Am I clear? Yes. Energy and momentum will give you the characteristics or properties of what? Streams of particles. What about the other 2 parameters, that is nu and lambda, frequency and the wavelength, are going to represent what? The properties of the traveling wave, and it is associated with the particle, obviously. Okay, that is, in some cases we'll take it as a particle, in some cases we'll take it as what? Traveling wave. Okay, if particle is there, associating wave nature is going to be present. Please keep it in mind. Hope I am clear. Now, what this frequency is going to represent? we can very clearly see the frequency is going to represent variation with respect to time. And what about lambda is going to represent with respect to distance, obviously, because we know in the previous tabular column we have very clearly given, no, we need to consider variation with respect to what, distance and time, and that is what we are going to consider here also. Okay, okay, let me write two more important points here. Okay, so what is that? The nu represents, that is frequency, represents variation, okay, variation with respect to, let me write it in short form, WRT, that is with respect to what, time. And what about lambda? What about lambda? It is with respect to distance. So represents variation with respect to distance. Okay, because both we want. So one parameter is representing variation with respect to time, the other one is with respect to distance. Okay, now let us consider these two equations and we'll get one important relation here, mathematical equation, where you can expect the problem also. Okay, let us consider E is equal to h in u. Okay, now we know very well what is the relation between the frequency, wavelength and the velocity of light. Yes sir, we can consider that relation here. What is that? Nu equal to what? C by lambda or V by lambda. Anyhow, C, what is C here? Velocity of light. So what is C here? It is 3 into 10 power 8 meters per second. Yes, okay. 3 into 10 power 8 meters per second. Or in terms of centimeters, if you want to write, 3 into 10 power 10. Okay. And what is h here? Planck's constant. What is the value of this? It is 6.626 into 10 power minus 34 is the value of h. Okay. Now put this nu into this one. Okay. So what is the variation that I'm substituting here? E is equal to h into c by lambda. Okay. So you substitute and find out the value. Okay. Substitute h is equal to what? This one. Okay. H is this one. C is this one I am putting. Okay. Then you can get the relation. So this is going to be, I can say, lambda in micrometers. If you write, it is going to be 1.24 divided by energy in electron volts. Or if we want to write it in angstroms, lambda in angstroms is 12400 divided by energy in electron volts. Okay. So any one of these equations you can use it. Okay, either the wavelength you can represent in terms of micrometers or in terms of angstroms. And what is 1 angstrom? Yes, what is 1 angstrom? Is 10 power 10 meters. Please, this conversion is also very important. Okay, many times in the problem when you are substituting in the mathematical terms, okay, there is a possibility that one parameter is in centimeters and you may substitute in other parameter in meters. Okay, so you have to convert. So keep it in mind. This is also very important. You may know the formula, but finally you are going to get a wrong answer. You need to take care of what? This units and dimensions. Okay, hope I am clear. So this is one important relation that you must remember. Okay, or vice versa also you can write energy in electron volts equal to 1.24 by lambda in micrometers. Okay, so one is I am representing in micrometer. Using this you convert this, you can get this relation. Okay, so you try to remember any one, other you can easily get it. Is it fine? Okay, hope I am clear. Now let us solve a problem based on this relation. Okay, let us take a problem, write it on, you can write with me. Okay, so what is the wavelength? You can take the problem. the wavelength of the light, the wavelength of the light radiated from, please take it down, radiated from gallium arsenide, okay, which is a direct band gap semiconductor, okay, gallium arsenide laser. What is meant by laser? Light amplification by stimulated emission of radiation, okay. Gallium arsenide laser is 8670 into 10 power minus 10 meters. Calculate the energy gap. Calculate the energy gap of gallium arsenide. Yeah, please try to calculate this. Direct substitution of the formula only. Direct substitution. What is the formula now? I can say energy gap in electron volts is equal to what? So given 10 power minus 10 meters, no? Can I say it as 1 angstrom? You write correspondingly that 12400 divided by lambda in angstroms. So this is 12400 divided by simply 8670. Just calculate. Should get this value as 1 electron volts. Simple substitution, okay. Hope I am clear. Now let us take another problem based on the same relation, but it's not straightforward. Let us take another one, please. You can take simultaneously when I am writing, okay. A photon of wavelength, a photon of wavelength 1400 angstroms, that is 1400 angstroms, absorbed by, okay, absorbed by mercury, okay, it's a material, mercury, radiated 2 photons, out of which one is having a wavelength of 1850 angstroms, okay. Calculate the wavelength of the second photon of the second photon. Yeah, please try to get the answer. Try to get the answer. So how you can calculate? What he has given? One photon has been incident on the mercury and it is absorbed, okay, but by the material, and another photon, there are 2 photons that are going to be radiated out of this mercury after absorbing the initial photon. So one photon wavelength is given. He is asking what is the wavelength of the other, okay. So here it's very simple, okay. So try to understand. Now let us take, this is mercury, okay. Now what we are doing, we are making a light energy to incident on this, okay. Let us take, this is the photon that is incident. What is the wavelength that is given here? It is 1400 angstroms, okay. Now what happened? There are 2 photons that are emitted, okay. One photon is having 1850 angstroms, the wavelength. Okay, and we need to calculate two photons are radiated, out of which one is given. This you have to calculate. Am I clear? Okay, now let us take, this is lambda. Okay, and what about this? This you can take it as lambda 1, and lambda 2 you have to find out. Am I correct? Okay, now let us consider the corresponding energy of the incident photon is E. Okay, let us write it is an electron volts obviously. Then what about here? Let us take the energy, okay, of corresponding to the photon 1 is E1. Then the energy corresponding to the photon 2 is E2. Yes, now we can very clearly see that this is the incident radiation or energy E, and it has to be sum of these two. Assume that there is no loss. Okay, obviously if take it as what, there is no loss in the material. Okay, then can I simply write E is equal to E1 plus E2? Am I correct? E is equal to E1 plus E2. Now you can calculate what is this E, because I know lambda. I can calculate what is E1 because I know lambda 1. Once if I, you can get E2. Once you get E2, you can get lambda 2. As simple as that. Okay, so let me find out what is E. Anyhow, in electron volts is equal to what? Because it is in angstroms, it is 12400 divided by lambda in angstroms. So 12400 divided by 1400. So this will give the energy E will be 8.857. 8.857. Okay, electron volts. Anyhow, I have written in the brackets. Don't worry. Okay. Then what about E1? What about E1 in electron volts? Again, it is 12400 divided by lambda 1 in angstroms. So it is 12400 divided by, what is lambda 1? 1850. So calculate this value. This will give 6.7 electron volts. Okay, now from this I can get what is E2. E2 is E minus E1. So E is how much? 8.857 minus 6.7. So which will give 2.157 electron volts. So once if I know E2, I can get lambda 2 now. What is lambda 2 now? What is lambda 2? Yes. What is lambda 2? I can write, because it is in angstroms. Let me write. It is in angstroms. 12400 divided by E2 in electron volts. So 12400 divided by what? E2 is how much? Just now we have calculated 2.157 electron volts. So you calculate this value, we'll get 5749 angstroms. Okay, so this is how you can solve the problem. Okay, in this problem, previous problem, it is straightforward, but it is not. We need to understand the other things. Hope I am clear. Okay. Yes. Okay. So this is about the very basic concepts that we have considered here. So what we have, I just briefly recapitulate whatever we have discussed now. We have started with what? Types of semiconductors. Then we have understood what is meant by equilibrium, and then we have discussed about the steady state, and we have discussed about the wave particle duality, and based on that, we got some important mathematical relation. Okay, yeah, you can expect the problems. There are many times question has been asked from this. Okay, there are only two parameters. Either you can give the energy and ask you to find out the wavelength, or wavelength is given, ask you to find out the energy. Okay. Yes. Or you can manipulate the other information, and you can ask you to find out the remaining parameters. Okay. So hope I'm clear with this. So here, okay. If you have any doubts now, we'll discuss. Okay. If you have any doubts, you can you can ask me. One important request from my side is, once your doubt is get clarified, please down your hand. Okay, because I cannot remember for whom I have clarified the doubt. Okay, so once your doubt is clarified, please down your hand. Okay. Yeah. Yeah, Nitish Kumar.
Hello, good morning, sir.
Very good morning.
Sir, page number 12, sir.
12. Yeah, fine. Go ahead.
Sir, why energy and momentum represent properties of particles in streams?
Why?
Hello?
You just think.
Why?
For a particle, what are the things that are going to be there for a particle? Particle means what you are going to have. Have you studied, in your physics, +1, +2 physics, have you studied about the collisions?
No, sir, I didn't remember.
You didn't remember? My God.
Yes, sir.
See, when collision happen between two particles, what will happen? There is an exchange of energy and momentum, no?
Yes, sir.
So it's a nature of particle, no? It's a characteristic.
Okay, sir.
Is it fine?
Yes, sir.
Yeah, good. Then, please, Prajakta, please go ahead.
Hello.
Yeah, Abhinash.
Good morning, sir.
Very good morning. Yeah,
Sir, can you go to page 10F?
10F.
Yes.
Fine. Yeah.
Sir, can you give an example of such process which is in steady state but not in equilibrium?
Yeah, we'll go when we are discussing about the devices, you can understand.
Okay, sir. Another doubt. Sir, you said in equilibrium that there would be an means.
Yeah,
within
Avinash, there is a
the
lot of disturbance behind you. Please, you can move out of that place. There is a lot of disturbance. Someone is shouting there.
so now it's okay.
Yeah, fine.
Sir, in that equilibrium,
Hmm.
sir, you said that some within the semiconductor there would be a means equilibrium. So can you explain that one?
Within the no. Within the semiconductor, when you are talking about the equilibrium, it is with respect to the environment, please. Okay.
Yes.
What I have given is the process that is going on between the semiconductor and environment. Okay, we have given that there should be an inverse process.
Yes.
Okay, and at the same rate, it is also applicable within the semiconductor also. Suppose within the semiconductor, from one point to the other point, there can be a transfer of charge.
Okay.
Yes or no? But from point 2 to point 1, same thing has to happen. That is what inside or within the semiconductor means.
Okay.
Is it fine?
Yes. Thank you, sir.
Okay, good. Yeah, Shiv Naik. Shiv Naik.
Hello, good morning.
Yeah.
Sir, in the same equilibrium state, you said there is.
Yeah, please move from that side. Okay, I think nearby you there someone is shouting there. Please.
Sir, no, I think it's. Hello.
Yeah, please.
Sir, can you hear me now?
Yes.
Sir, you have given this no, sir. It is also applicable for the process within semiconductor. You have given no, sir. And you have also given this second statement. There is no net transfer of energy or charges.
Yeah, to
So
check
in-
it. Yeah.
Yeah, in the semiconductor, if the movement happens, then the suppose
Yeah.
if movement happens within the semiconductor, the charge also will happen, no, sir.
Yeah. See what is the second statement? Please read once it is.
There is no net transfer of energy.
I am not saying that no transfer of charge, okay, or energy. What I am talking? The important word here is net. Net means what? Suppose transfer, because once your temperature is more than 0 Kelvin, always there is a random motion of the charge carriers.
Yes.
But there is no net motion. Because of that, you don't get any current.
Okay.
Are you understanding?
Yes, sir.
The net transfer is important here. Okay, I'm not simply saying no transfer of charge or energy. What it is? Net transfer of charge or energy. That is important.
Okay. Sir, again,
Yeah.
payment 5F, sir.
5F. Fine.
You have given the statement, no, sir, at the last one for intrinsic semiconductor. This is possible only when one impurity compensates the other impurity. At that point, I did not get, sir.
See, suppose because of one impurity, there are some positive charges that are going to be present. For example, you take some holes has been created because of some impurity.
Okay.
Okay. Now, if some other impurity is not compensating these holes, definitely you don't get the same number of electrons or holes as the pure semiconductor. No. So corresponding negative or electrons has to be, that holes has to be compensated by some other impurity. Then only it is possible.
Okay. Sir, like what is impurity example, sir?
Impurity. What is impurity, man? Suppose you consider your body, anything which is other than what you are considering is impurity. Suppose you take, for example, germanium.
Okay.
You replace one atom with some other particle or some other atom. It is impurity.
Okay.
Fine.
Okay. Okay, sir.
Fine. Okay.
Yeah.
Yeah. Yeah, Shivasai.
Yes, sir. Sir, page 8, sir.
Page.
Hello?
Yes, page number
8F, sir.
8F.
Yes, sir.
Yeah.
Sir, can you give an example which is having temperature excitation, but it is in equilibrium?
I'm not getting temperature excitation. Yeah, please think on your own, man. Let us think on your own. Spend some time at least.
Sir, when there is a temperature difference, there will be definitely a heat transfer, no, sir?
Obviously, that's why it is not in equilibrium.
So once there is a temperature difference, we can call it as an equilibrium, but you wrote there
No, please. Equilibrium means these two conditions has to satisfy. Please remember, we have given condition 1, condition 2. No. If both the conditions are satisfied, then only you can say it is under equilibrium condition. Are you getting my point?
Yes, sir.
Okay, both the conditions has to satisfy. In this case, the first one is satisfied, but second condition, it cannot be satisfied. No, definitely there is a transfer of energy. I think you don't get the first condition, what you have asked. No, there is a difference in the temperature and equilibrium. I think up to my knowledge, it's not possible, because definitely there will be transfer of energy and charge.
Yes, sir. Yeah. Sir, another doubt, sir. Sir, let's say there is a gallium arsenide crystal.
Fine.
And its band gap is 2 electron volts. Once I applied 2 electron volts, it released a wavelength. It emitted a wave of wavelength lambda.
Fine.
Another time I applied 4 electron volts. Will be another wave also emitted. So will the wavelength will be the same in both cases?
It may or may not be. It's not necessary. Because whatever 4 electron volts that you are applying, it may or may not go complete 4 electron volts. No. There are many other things that you have to consider. May or may not be.
Sir, in that case, the
Ah.
problem we did will fail, sir.
Which problem?
So that wavelength in laser, gallium arsenide laser.
Gallium arsenide. Yeah, see, the problem that we have solved, whatever we are assuming, default we'll assume that there are no losses. Are you getting?
Yes, sir. Yes, sir.
Default we'll assume that there are no losses. If we specify specifically this much of loss is there within, within the material, then the second problem that we have solved, no, it will be different. You have to subtract that losses from the total energy, and then you have to distribute that energy to the two particles, waves.
Oh, okay, sir. Fine, sir.
Is it fine?
Thank you, sir.
Yeah.
Yes, sir.
Fine. Yeah, Rayavelu, please. Sorry, Rajavelu. I'm sorry.
Hello, sir.
Yeah,
Sir, page number 7.
page number 7F. Yeah.
Sir, could you please explain me again the principle of detailed balance? You used
Yeah, I
some
explained
example.
3 to 4 times, man.
3 electrons mass one like that. The
Okay,
mass of the electron will be same, no, sir, for all.
No. For a macroscopic level, when you are seeing, we are taking it as same. But if you consider the effective mass, all you consider any semiconductor parameter that we are going to consider, it is going to be the average values. It's not a absolute value, not one particle that you are going to consider. There are many particles. Take the average. That is what we are going to do. It's not single value. Maybe the difference may be very minute for us. 0.0001 difference will be there, but still it is for that particle it's going to be different. Are you getting my point?
Yes, sir. So it's called detailed balance, sir.
Yeah, because that is what I have given. No, principle of detail means microscopic level also you have to observe.
Okay,
But anyhow, for us, for our discussion purpose, it's not required. But you must know. That's why I have given that point.
Sir, thank you, sir.
Yeah. Yeah. Seshank. Shashank, please respond. Swaroop.
Good morning, sir.
Very good morning.
Sir, in 8F.
8F.
Sir, can you explain the case 1?
Case 1?
Yes, sir.
Yeah. See here, semiconductor, two ends have two different temperatures. Fine?
Yes, sir. Yes.
Now T2 is greater than T1. Obviously, what will happen? What is the energy of your, at this side 2? Let us take this is side 2 and this is side 1.
Yes,
then
sir.
Definitely this side 2 is going to be at the higher energy than this side 1, no?
Yes, sir.
And obviously there will be a transfer of energy.
Yes, sir.
Then you check the condition 1, you check there is no external excitation other than the temperature. Yeah, that is satisfied. Clear?
Okay. Yeah. Yes, sir. Fine.
But what about the second? There is no net transfer of energy or charge, but there is a net transfer of energy or charge, no, from this.
Sir, but then whenever there will be a temperature excitation, there will be a net transfer of energy, no, sir?
That's why it is not in equilibrium. That's what I'm asking. I'm explaining you. If
So
there
then
is-
the condition 1 is contradicting condition 2, no?
No. It's not contradicting, man. That's what I very clearly mentioned. Both the conditions. See, you see, clearly read this. The semiconductor is in equilibrium if 1 and 2, both the conditions are satisfied. Both the conditions has to satisfy. Then only it is going to be under equilibrium. If any one condition is not satisfied, no, it is not equilibrium.
Okay.
Is it fine?
Yes, sir.
Both the conditions has to satisfy, not one.
Okay, sir.
Okay?
Okay, sir. Yes,
Yeah.
sir. Thank you.
Okay. Yeah, please, the doubts, who got clarified, please down your hands, okay? So that I can. Yeah, Divyansh.
Good morning, sir.
Very good morning.
Sir, I have a doubt only at this page.
Which one? Which 8F?
This page, the equilibrium thing.
Yeah, please.
Sir, the first statement says that there is no external excitation other than temperature.
Fine.
So can we say that we are not providing external excitation when a semiconductor device is, we are providing it temperature, like uniform temperature,
No,
and we are heating it.
you need not to provide a temperature, no, because what is the ambient condition for any material? For us also temperature is
Room
obviously
temperature.
obvious. May not be room temperature, maybe different temperature also. But whatever you are giving, obviously there will be a temperature, no, surrounding that device or object. Certain temperature will be there, obviously.
Sir, suppose we have certain stuff that is temperature sensitive, then its property is going to change, na?
Obviously
Like
changes, temperature sensitive,
so
obviously.
these properties change due to external excitation, or
Which property?
Suppose resistance.
No, see, I'm not talking about resistance here. Please confine to what we are talking, no, because it is equilibrium I'm talking here. Where come resistance came? I don't understand, because if you see, if you mix so many things into one where it is not related, there will be a lot of confusion. Why you are taking resistance? Please tell me.
Sir, my doubt is just why temperature is not included in external excitation. That's it.
That is default, no? Can you isolate from the temperature?
No, sir.
Yeah, that's what it is, default.
So heating is not external excitation.
No, heating is different, man. Please, you are again getting confused. Heating means you are again giving, no, anyhow.
Okay, sir.
But suppose if I am sitting in a room, surrounding me there is a temperature, no?
Yes, sir.
Are you giving that? Actually, it's a natural thing.
Yes.
Are you understanding?
Yes, sir. Yes.
Yeah. Then if you intentionally you are giving some other excitation, that's a different thing. Okay.
Okay, sir.
Yeah. Any other doubt?
No, sir. No, sir.
Yeah. Thank you. Yeah, Harsha.
Hello, good morning, sir.
Very good morning.
Sir, am I audible?
Yeah.
Sir, my doubt is that when we take an extrinsic, like if we take a semiconductor material and if we add an impurity, then it will be an intrinsic, no, sir?
It will be?
An extrinsic semiconductor, no, sir?
Obviously.
So, how can you identify whether the taken material, material is pure or intrinsic?
Pure or?
Intrinsic.
Yeah, that's what I have given, no? See, in intrinsic.
No, sir, if we take a material like semiconductor material,
Fine.
or germanium, so how can we know actually that is a pure?
See, pure is going to be ideal condition actually. You don't find any pure material, because if you consider the surface, maybe 1 second, I'll maybe that point of time I should have explained. No problem, don't worry. Suppose I'll write here. See the suppose this is the bulk, if I call, for example. Okay. This is the bulk I am calling. Surface is going to have lot of impurities and lot of discontinuities. Okay, any surface you take, okay, there will be lot of impurities and lot of discontinuities. So if I call as a bulk, we are going to exclude this part. Okay, this is the surface, no? So this part you are not supposed to consider. Okay, only this part we are going to call it as the bulk. Am I clear?
Yes, sir.
Okay, yeah. Any other doubts?
No, sir.
Okay, thank you. Akila Reddy, please.
Hi, good morning, sir.
Very good morning.
So, can we say that all intrinsic semiconductors can be in either equilibrium or steady state until and unless an external excitation is applied?
Obviously, because that is the first condition that we have given to satisfy the equilibrium condition. When you apply external excitation, it's non-equilibrium. Whether you intrinsic or extrinsic, anything, it's going to be non-equilibrium.
When we apply external excitation, intrinsic can also become extrinsic semiconductor.
No. That is different. Intrinsic will become extrinsic only when you dope with a particular, specific type of impurities or, dopants. That is different. This is different.
Okay, sir.
When you apply the external excitation, how it will become extrinsic? I mean, intrinsic will become extrinsic. It's not possible. Are you understanding?
Because I mean the bonds may break between the.
Because of that, electron hole pairs are going to be generated. That is a different thing. You are modulating the electrical properties,
okay,
but not its basic nature. Okay. Basic nature is intrinsic.
Okay, sir.
You may generate extra charge carriers. That's a different issue.
Okay.
Is it fine?
So, equilibrium can be disturbed either by external excitation or by doping.
Please, again, you are mixing two different things. Doping, why you are using doping? To disturb or to modify the basic characteristics of the material you are doping. Once you have modified these basic characteristics, you are using for a certain purpose. Then you are applying some external excitation. Are you understanding my point?
Okay, it means doping cannot disturb a equilibrium state or steady state of a semiconductor.
See, why you want to make some conclusions? You are taking two independent things and you are mixing. Are you understanding my point?
Yeah, sir.
Doping, please try to concentrate. What I am explaining is doping is going to change the basic characteristic of the material. The external excitation is not going to change the basic nature.
Okay.
Are you understanding?
Okay, sir.
That's what I tell you. Suppose you take the intrinsic semiconductor material, when you apply some voltage, it will not become extrinsic. But when you apply the voltage, it is a. Why you are applying external excitation? To modify some electrical properties or something you want to get out of it, then you are applying external excitation. So these are two different things. Don't mix it.
Okay, sir.
Got it?
Yes, sir.
Yeah.
It means intrinsic semiconductors always has equal number of electron and holes.
Obviously.
So it is always in equilibrium state, no, sir?
With respect to what? That's what I am telling you. See, for suppose even that's the example I have taken. No, here third example. You see the third example here. That what we have written there. Third example. Let us take this semiconductor is an intrinsic semiconductor.
Yes.
Okay. Then you are applying external excitation. It is non-equilibrium condition.
Okay.
To conclude in general, okay, it depends on the situation.
Okay.
Are you getting my point? Okay.
Right, sir.
Okay. Yeah. Yeah, Krishna.
Hello, sir. Hello,
Yeah.
sir. Can you hear?
Yes. Go ahead.
Can you please go to page 10?
10F.
Yes, sir.
1 second. Yeah, I think from your side there is a lot of disturbance.
Hello, sir. Now.
Yeah, your voice is audible, but there is a lot of disturbance. Fine. Yeah, tell me.
Oh, sir, here can you please give me how equilibrium conditions are satisfied, sir, and how you concluded that it is steady state? That I didn't get it, sir.
Yeah, you need to spend some time, and it will not get that much easy. You have to spend some time. But anyhow, I'll explain. Please listen carefully.
Yes, sir.
See, the bigger circle is what? Steady state, no?
Yes, sir.
The smaller one, that is blue color, is the equilibrium.
Yes, sir.
Now you consider area under the complete red circle. Can you take it as steady state? Complete area. This one.
Actually, I didn't understand, sir. How Volcan?
What you are unable to understand?
How can you tell that area under this is equilibrium?
That is what we are taking. No, see this circle we are taking it as steady state. No. This entire thing is steady state.
Okay.
And one important point here is for to make it your equilibrium, there is one condition that we have given. What is that?
No external forces energy should be applied and
no man, you are mixing, not that one. Very beginning we have given one important conclusion. that for every process that is going on, there should be a reverse process.
Yes, sir. Yes, sir.
Yeah, but in case of steady state, it is not required.
Okay.
From that, actually, we have drawn these two. This the equilibrium is going to be the subset of steady state.
Always, sir.
Always. Yes. Yes.
Okay, so so whenever it is in steady state, it will be in equilibrium, but not vice versa.
No. When it is in steady state, it need not be necessarily under equilibrium.
Okay.
But if it is in equilibrium, it is definitely under steady state. See, I'll explain why. See, whatever point that you are going to consider within this red circle, it is in steady state. Am I correct? Okay. So let us take with suppose this is the point I am considering 1. Okay. So this is in steady state. This is all sorry. This is steady state. This is also steady state. Now let us take what about this one? Let us take point 2. Point 2 is in steady state.
Yes.
Yes, obviously. And also within this circle, blue circle, whatever the point that you are going to consider, only within the blue circle, it is in equilibrium.
Okay.
So it is both in steady state as well as equilibrium. But suppose if this is the point 3 you consider. Now this is only in steady state, not in equilibrium. Not in equilibrium, but it is in steady state.
Okay. So these are just we considered as an example, right, sir?
Means what? Yeah, to make you to understand, I have given point 1, point 2, point 3. Yeah.
Okay. I thought that every time the semiconductor will inside will be equilibrium, outside will be steady state, sir.
That's what I am telling you. That conclusion we made now here. This statement what I have given here. This is always it holds. This statement whatever I have given, it always holds.
Sir, and how can we say that it is steady state by looking at a semiconductor, sir?
Not by looking. It has to condition. No, we have given very clearly here. This definition
function of time.
Yeah. By taking these definitions, you can understand whether it is in steady state or not, whether it is in equilibrium or not.
But equilibrium directly we are telling it now, sir. As there is no external, we are not applying. There is no exchange of energy, and there is no difference.
I got your point. There is no need for the steady state. No, directly there is only one thing here. If it is changing with respect to time, it is not in steady state. If it is not changing with respect to time, then it is steady state. That's all.
Also, we need to consider intervals of time and measure its activity.
No, not intervals of time. Why you are again you are getting confused. Don't worry. Simple statement. If any parameter is not changing with respect to time, then you can say steady state. If the parameters are changing with respect to time, it is not in steady state.
Not in steady state. Yeah. Sir, and you told that there is no net exchange of energy means net exchange is 0, sir.
Yes.
Net energy is 0, but there is an exchange of energy.
No, not net energy. Please use your words very carefully. I have written no net transfer of energy, not net energy. Net energy is different. Net transfer of energy is different. Are you getting my point? No net transfer of energy is different. I am not saying no net energy. Transfer. There is a word transfer. That is important.
Okay. So there is an energy transfer, but there is no net energy transfer, right?
Obviously. Whenever there is a temperature more than 0 Kelvin, definitely there will be a transfer of energy.
Okay. So last doubt, sir. Yeah. So that last problem can be solved by E equal to hc by lambda formula, sir?
Yeah, you can solve it.
Okay, sir. Thank you very much, sir.
Yeah.
That's it, sir.
Yeah. Shubhi Jain. Yeah, please make it fast because again I have to answer almost 20 questions, please.
Hello.
Yeah.
Hello, sir.
Yeah.
In page number 5F.
Yeah. 5F.
Sir, you told, in pure semiconductor there should not be a defect and impurity. And in intrinsic semiconductor, you told there can be some, but number of electron and hole must be same as that of pure semiconductor. How can it possible, sir? The number of impurity means concentration will be increased. In intrinsic semiconductors.
Yeah, along with that I have given one statement. After that you read it.
Yes, sir. This
In
pure.
the statement, last line, I have given one more point. There
Yes,
can
sir.
be what is that? Please read it once.
This is possible.
Read it.
This is possible when. This is
Only when
possible only when
one
impurity
impurity compensates the other.
compensate.
That this indicates this gives your answer for your question. No, suppose for one impurity somehow there are holes has been increased, for example.
Yes, sir.
So other impurity, what will do? It will make that holes to reduce to the equilibrium, whatever the
Okay.
values are having for the pure. That is how. That is the reason why that is also important. The continuation.
Sir, if this compensate that, then that means there should not be any impurities.
No,
Only
see, please,
compensation.
no, please try to understand. Impurities are present, but one is compensating the other, means the net effect is going. But physically, impurities are present, no.
Okay.
Are you understanding?
Physical.
Physically,
Okay.
impurities are present, but characteristic wise, if you go, then it's a different issue.
The characteristic, like it will be equal to pure semiconductor.
See, pure, actually, you don't find any pure material. You don't find. It's a reference for us, okay? It's a reference, and that is what I have explained. Suppose see that I have drawn here one. So the blue color is actually your semiconductor material, but the surface is going to have even inside the material, if you consider, and the surface of the material you consider, you have more impurities and discontinuous at the surface more than in the material, within the material. So what we are going to do is we are going to exclude actually this part. That dashed line I have given, no, only inside this we are going to call it as what? Bulk.
Okay.
But anyhow, practically, or in reality, you don't get pure. Not only semiconductor, anything you consider pure, it's a reference for us. Like,
So this bulk is pure, sir.
we made it, no, but what about the other part?
This will be called intrinsic. Because
You are just you are making changes, okay, which are going to be very close to that pure semiconductor or ideal characteristics.
Okay.
But you never reach that, okay, but you have to try reaching that ideal value.
Okay, sir. Got it, sir. Thank you.
Okay. Charan, please. Charan, please respond fast. Charan. Sandhya. 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 Yeah, Varij. Varij.
Hello.
Yeah.
Good morning, sir.
Very good morning.
Sir, in page 12F.
Yeah, your voice is breaking.
Sir, in page 12F.
12F. Yeah. Please go ahead.
Sir, one angstrom should be 10 to the power minus 10 meter, na?
Oh, okay. Sorry. Yes, I'm sorry. It should be 10 power minus 10. I'm sorry. Please change this modification. 1 angstrom is 10 power minus 10 meters. I'm very sorry. Okay. Yeah. Any technical doubt?
No, sir.
Yeah, thank you. Thank you.
Thank you, sir. Okay.
Hello.
Please mute your voice. Yeah, please make it fast. Respond fast.
Okay.
Yeah, please Those who got doubt clarified. Yeah, someone voice is coming. Please unmute your voice.
ठंडा है ना दही
Yeah, Akila Reddy, please go ahead. Akila Reddy, please go ahead. Akila Reddy.
Because she comes out with a performance so strong that ఆమెను చూస్తుంటే పక్కనకి ఎవరిని చూడలేము. So నాకు I had a concept.
Yeah, Abhishek.
So good morning, sir.
Very good morning.
Sir, in the equilibrium concept, now suppose for a semiconductor, if I apply 100 degrees Celsius to, uniformly to the semiconductor, then semiconductor be in equilibrium or not?
Yeah, you tell me.
Sir, in 100 degrees Celsius, the must be very random, sir, because of very high energy. Then how can we tell that internally itself,
Now you tell me whatever the condition that you have given, will it be equilibrium or not?
Sir, according to the condition, it should be, but how can we predict, sir? Like inside the molecule itself,
inside the molecule, what will happen?
Like suppose I give energy to an atom, it goes, from one orbit to another orbit. Same reverse process it occurs on. How can we guarantee that, sir?
I'm not getting. Inverse means what? See, you are okay. I got your point. See, you are talking only about one particular electron. Suppose.
Yes, sir.
There are other electrons. No, at the same time, there is a possibility that in the reverse process that can happen. But that is the reason why I have very clearly mentioned there is no net transfer of energy. Please remember one thing: when your temperature is more than 0 Kelvin, always there is a transfer of energy. Okay, but what is the condition that we have given here? The word net is very important here.
Yes, sir.
Are you getting my point?
Yes, sir.
Net transfer is important. I am not simply saying no transfer of energy. It is net transfer of energy, no net transfer of energy.
Okay, sir.
Hope you got the answer, huh?
Yes, sir.
Yeah. Ajit Kumar, please respond fast. Ajit Kumar. Ajit Kumar. Chandu.
Hello, sir.
Chandu.
Hello, sir.
Yeah, Chandu.
Yeah, am I audible to you?
Yeah, clearly. Go ahead.
Sir, I have a doubt in page number 8F, sir.
8F, yeah, it is there.
Sir, here in the first example, you did not mention anything about the environment.
Environment, default
Temperature
what?
of environment.
Temperature of environment means what? What or how it matters here?
Is it, sir, if we can here, if you consider the system, one part of the system is having T1 temperature, sir.
Fine.
Other part is having T2 temperature, which is greater than T1.
Fine.
Here, there will be transfer of heat energy within the system, sir.
Fine.
But as system as a whole, it do not respond to the environment.
System as a whole?
It do not respond to the environment.
Why it is not responding to the environment? How you can say that?
Sir, here you did not mention anything about environment.
My question is, if I don't mention, how it is going to affect? That is what I am asking. Are you getting my point? If you suppose you consider some environment is there, how it is going to affect this answer or this particular thing? Are you getting my question? How it is going to affect? It will not know, because simply you check these two conditions. If these two conditions are satisfying, then you can say. If you are checking those conditions, okay, here it is not necessary that 100% every detail that you are going to have, but whatever details that you have, that you can check within this. And anyhow, default it is environment only, default. Suppose if you are sitting in a room, what you are going to have surrounding that you are going to have air, you are going to have temperature, everything. Moisture will be there. All these are going to be default conditions, no? Are you getting?
Sir, how did you say that it is not satisfying second condition? No net transfer. Is there a net transfer of energy?
Yeah, your voice is breaking and there is a lot of disturbance. Some air is coming, lot of disturbance. Now ask me how
Sir,
the second condition.
Is there net transfer of energy with the environment, sir?
With the?
How do you say the system is not satisfying the second condition, sir?
How do you say it is satisfying? Tell me.
Sir, within the system there will be transfer of charge, sir. But if we take the system is ideal to the environment, then it do not exchange any energy with it.
See, obviously there will be an exchange of energy, but you may not in a position to see that. Yes or no? Obviously there will be, because from one medium to other medium, there will be a discontinuity and there will be a transfer of energy will happen, definitely.
Which form of energy, sir?
What form of energy you are applying here?
Thermal energy.
Yeah, obviously that energy only. See, suppose you are heating, some water, and by keeping a container on the stove, you are heating the water. What will happen? Water will get heated. You move that out of your stove, switch off the stove, or you keep it there only. What will happen now?
Water
temperature will go, or it will be remaining the same?
Cools down.
No, that's what is here also it can happen, no? But what is your doubt? If that is happening, what is your doubt there? I'm not getting exactly what is your doubt.
I thought that system within the system there will be transfer of charge, but system as a whole it do not respond to the environment, sir. Since you did not mention anything about environment.
See, why? That's what I'm telling you, man. Default, what is this temperature is environment only, no? How come you got these temperatures? How come you got these temperatures T1 and T2? Are you understanding my point?
Some external.
Obviously you'll have some environment, but here my point is why you are thinking about the environment. Here your concentration should be about the semiconductor and things. Your focus should be here, not you are deviating. Are you getting my point?
Okay.
Yes.
Yes, sir.
Yeah. Good.
Yes, sir.
Yeah.
Sir, I have another doubt.
Fine. Go ahead.
Sir, if you take a pure semiconductor, and if we dope it with both p-type and n-type impurities, then such a way that the physical properties do not change, and the number of holes and number of electrons should be same. Then does it called as intrinsic because both number of electrons and number of holes are equal, or does it called as extrinsic because it is doped?
Yeah, anyhow, we'll discuss that in the compensated semiconductor once you start the extrinsic. Don't worry, okay? Here, there are two things which you need to understand. One is called, material property. Another one is the material nature. Are you understanding? Material nature, material property. Now, material property is going to be intrinsic. It will become intrinsic, but material, what you call material characteristic or material thing is going to be, it's going to be, because you are adding it, definitely like extrinsic only, but overall characteristics behaves like an intrinsic.
Sir, in practical applications, what do you consider, sir? Is it considered as a intrinsic or extrinsic?
Yeah, we'll discuss this point when you are discussing about the extrinsic semiconductor. Okay. We'll go in detail there. You can get the answers on your own there. Okay, fine.
Okay. Thank you.
Yeah. Jagadish, please go ahead. Yeah, please respond fast. Jagadish. Jagadish. Yeah, please, those who got answer, please unmute your voice, okay? Because some of the people are not unmuting, so I'm getting their voice also, okay? Jagadish is not there. Next, Anwar, please go ahead. Anwar. Anwar. Sharmila, please go ahead. Sharmila, please go ahead. Hello. Tejasri, please go ahead.
Good morning, sir.
Very good morning.
Sir, I have a doubt in page 7F.
Page 7F. Yeah.
Sir, actually your voice was breaking when you're teaching the example, sir. So I didn't understand how that example is related to that.
Which example? Which okay, principle of detail. Okay, yeah, I'll please concentrate. Sir. Yeah. See, we are calling this. No, disturbance is from your side, not from my side, I think. Okay, anyhow, principle of detailed balance is, suppose, I think I am getting a lot of disturbance from your side.
No, sir, here there's no disturbance. Some other ones.
Maybe, yeah, okay, fine. See, some 10 electrons are moving from semiconductor to environment you take. Okay? Yes. Now, out of this 10, 3 electrons are going to have mass of M1. Another 3 is having mass of M2.
Yes.
Another remaining 4 is having the mass of M3. When the, what is the condition? 10 electrons per second are moving from semiconductor to environment. Now, same 10 electrons has to come from environment to semiconductor, no?
Yes.
Within 1 second.
Yes.
Now, when the electrons are moving from environment to semiconductor, again 3 electrons should have M1 mass, 3 electrons should have M2 mass.
Okay.
The remaining 4 should have M3 mass. That is what called as principle of detailed balance. Anyhow, we don't look into that microscopic level, but this is also important. Maybe for your, when you go for your masters and all, this is also matters. Is it fine?
Thank you.
Yeah.
Yes, sir. Thank you.
Yeah. Ashwatthama, please go ahead. Please respond fast, and those who got doubts clarified, down your hand and unmute your voice. Ashwatthama. Ashwatthama. Srivalli.
Good morning, sir.
Good morning.
Sir, in page 8F.
8F, yeah.
Sir, in the first example, if both the temperatures on either side be same, will that be equilibrium, sir?
Will they?
Will that be
Yeah, you keep your mic very close to your mouth. I'm not getting.
Will that semiconductor be in equilibrium, sir?
When? What is the condition that you are giving?
If either side T1 only is there,
Will
that semiconductor be in equilibrium, sir?
Yeah, tell me whether it is equilibrium or not. You just check the condition,
Yes.
no? You check the condition. Is there any first condition is satisfied there?
Yes, sir.
What about second condition? Is there any net transfer? Second condition, is there any net transfer when T1 equal to T2?
Sir.
No, then it is equilibrium, obviously.
If we apply any heat from any heat intentionally, then it will be non-equilibrium.
No. That's what. See, temperature. I can have the temperature as the excitation. That's what the first point is giving. No, there is no external excitation other than the temperature. If any excitation is present other than the temperature, then blindly you can put it as non-equilibrium condition. But if temperature is the excitation, then you have to check for the second condition. If both the conditions are satisfied, you say it as equilibrium. Only if condition 1 is satisfied and condition 2 is not satisfied, again it is non-equilibrium.
Yeah, that means we can give temperature externally also.
Obviously. Okay. Yeah. Sridhar, please go ahead. Sridhar.
Sir, good morning, sir.
Very good morning.
Sir, actually yesterday one of the formula that is energy gap, but German name is 0.785 minus 2.23 into 10 power minus 14. No, sir. You have said no, sir.
Yeah.
In that, what we have to consider temperature, whether in degree centigrade or Kelvin.
Capital T is what?
Yeah, that's what. Whether it is a degree centigrade or Kelvin.
I think very clearly I have written, no, capital T is equal to small t plus 273. Tell me capital
yes,
T.
sir.
Capital
Okay,
T
sir.
degree Kelvin.
That's okay, sir. And once again, in the room temperature, you have taken 300 Kelvin. Yes, sir.
Yes, obviously. 27 degrees centigrade is the room temperature.
And once again, you have taken 0 degree. Capital T is equal to 0, no, sir?
0 Kelvin.
0 Kelvin.
Not 0 degree. 0 degree Kelvin or degree centigrade. That is important. Capital
okay,
T equal to 0 is called as absolute 0. Absolute
Yes, sir,
0.
yes, sir. So what I was thinking that capital T should be 273 because 0 plus 273. No, I'm thinking like
no.
Not the way, no, sir.
No. See, capital T is in degree Kelvin. It should be equal to small t plus 273. Small
Yes,
t
sir.
will give in degree centigrade. A basic
Yes, sir.
relation, no, I think you know, that's why I have not concentrated much on that.
Yes, sir. Yes, sir.
Fine. Okay.
That's it, sir.
Yeah. Okay. Thank you. Salman, please go ahead. Salman. Pavan Kumar. Yeah. Who is this? 1, 2, 3, 4.
Good morning, sir.
Very good morning. Can I know your name?
This is Mike.
Mike?
Yes, sir. Sir, I have a doubt in yesterday's class.
Oh, okay.
Sir, actually, the diagram which you drew for the carrier concentration, so you told up to 10 power 6 per cubic meter. If there are carriers, it comes under insulators, no, sir?
Fine.
So what I do, I start doping this, sir. Will it become semiconductors?
No, that's what we have very clearly given at the beginning itself, no? You may dope it, but its characteristics cannot change.
Characteristics like mobility and all, no, sir. But
mobility is different issue here. First, you need to consider how many number of electrons or charge carriers are present. That is important. Mobility and all are the secondary cases. See, once you have the charge carriers, then mobility things will come. If charges are not there, where come mobility will come?
That's what I start doping and giving it charge carriers, sir.
You are doping, but can you create the charge carriers? That is what I am asking you.
With external excitation, it's not possible, sir.
How? It's a material property, man. With external excitation, you can able to move. Once the carriers are created, by applying the external excitation, you can move them. But with the external excitation, suppose you consider the light energy, then you can generate. That's a different issue. But for your metal or particularly insulator, if you remember the energy band diagram you have given, no?
Yes, sir.
If I want to make the free carriers, you have to give 6 electrons of 6 electron volts of energy, so that electron from the valence band can move into the conduction band. But practically that energy cannot be withstood by your material, so you cannot make it. And you are talking about the doping, but doping may not result in the carriers, charge carriers.
Okay. Sir, and when we give light energy with a frequency V1 and after recombination, again it gives back with a frequency V2, which is V2 less than V1, no, sir, in photo.
Yeah, new one, not V1, it is new. Yeah,
mu1,
new one, new two. Yeah.
So, is there a relationship between mu2 and mu1, sir?
Yeah, you can get it. I think it's not required for us. I am not discussing that much. That's what I told you very clearly. You need to require some background of physics and chemistry initially. Okay, so whatever we want, I'm concentrating here. You further, if you want, you go and refer those textbooks.
So it can act as like a frequency divider, which we use, sir.
No,
something like a frequency divider.
Frequency divider concept is different. Here you have two different frequencies. That's all. Frequency divider is different.
So exactly, if we keep giving V1, we won't get exact V2 all the time, no, sir.
Yeah, but ideally we'll take it as some cases same, but practically there will be loss within the material. No, obviously there will be loss.
Yeah, that's it, sir. Thank you, sir.
Yeah, thank you. Neelansha, please go ahead.
Hello, sir. Am I audible?
Yeah, go ahead.
So actually, I have a doubt in that intrinsic part. In this, you told that impurity compensates the other impurity. So I just want to ask which impurity we need to consider here. Like in extrinsic, for PNN, we consider group 13 element and group 15 element as an impurity. But
okay, go ahead.
But sir, here in intrinsic, we didn't dope any material. So how can we get the impurities as
impurities are part of your material, okay? Impurity or defect is part of your material. But in case of extrinsic, we are calling impurity as your, one type of impurity is your, third group and fifth group elements.
Yes,
but even if you don't dope with them, you have some of the impurities which are going to be present in the material.
In the material itself, but sir, how can we, if the impurities is present in the material itself, then how can we compensate that impurity with some another impurity?
You are not compensating. It's a nature. The material itself is getting it. That is what we are calling it as in. You are not at all disturbing any condition. Okay, please remember it. In intrinsic, see, pure is actually the ideal condition, I can say.
Yes, sir.
Ideal. Practically, you don't get pure. Any not only this one. Any material you consider it's not pure.
But sir, if any material we consider as an intrinsic, like any material I'm considering, you are saying that there isn't some kind of impurity there.
Obviously.
But how can you say that one impurity is compensating the other impurity?
Otherwise, it is not an equilibrium. Your system will not exist.
Okay.
Your system will not exist. Suppose you take in a particular material, there are 10 electrons and only 5 holes, for example, or 10 positive charges.
Yes, sir.
Physically, it is not going to exist. Physically, it is not going to exist.
Okay, so there should be some equal number of electrons and holes.
Obviously.
For intrinsic and extrinsic both.
Yeah.
Okay. And sir, yes, sir. And sir, in one more doubt. In steady state, you are saying that if parameters are not changing with respect to time.
Which one?
Steady state.
Steady state.
Parameters are not changing with respect to time, then it is in steady state.
Yes.
The system is in steady state.
Yeah.
And you are saying that if semiconductor is in steady state, it need not necessarily be under equilibrium. But it may or may not be in equilibrium.
Yeah, it may or may not be. Yeah.
But sir, if I am considering that semiconductor is in steady state and it may be in equilibrium too, so my system doesn't exist, right?
Why your system is not existing?
Because you said that semiconductor devices are not useful. Like that isn't useful for us.
See, suppose you how to explain this? Suppose you take a PN junction which is open circuited condition.
Yeah. Okay, sir.
It is both under steady state as well as equilibrium.
Okay.
Yes or no? Because you are not applying any external excitation. All the concentrations are equilibrium. But still your system is present. But you may not be in a position to use it. That's a different issue. You cannot say system is not existing.
Can I consider that whether the system is in off state, like the P injection is in off state, then we should consider
off
it.
State is again when you are using technical words, be careful. Off is different again. It is in equilibrium or open circuit or zero bias condition. Off means it is you are applying actually reverse bias, no? Because off switch is what? That's a
Yes,
different
sir.
issue again. That's a different you. Okay.
Okay. So sir, I didn't get.
See, if I say, if you are saying off, what is the meaning of off actually?
Like we are applying the reverse biasing.
But it is not in equilibrium, no? Off means you are applying reverse bias. It is not equilibrium.
We are applying some external supply.
But
Yes,
what I am
sir.
saying is equilibrium means you are not applying any bias, zero bias condition or equilibrium or open circuit. That is a different issue. That's what. Okay.
And so you told one more thing, that quasi-equilibrium situation.
Quasi-equilibrium.
Which one is this?
Which one means?
Like I didn't get the concept.
Suppose
that
you
many,
apply
you
from equilibrium, you apply some forward voltage. So it is small deviation from the equilibrium condition. Very small deviation from the equilibrium. Then you can call it as quasi-equilibrium. Whatever we have done for the equilibrium analysis, we can extend to the even for quasi-equilibrium. Fine.
Okay. Yes, sir. Yes.
Yeah.
Yes, sir. Thank you.
Okay. Yeah, we'll break for 15 minutes. We'll come back and discuss. Come back. Now we have seen the basic concepts. Okay. Now let us move to the next topic. Okay. Please, one small request from my side. Okay. So those who are asking the, raising your hand, if already the doubt is asked, okay. So I think you can, the doubt is already get clarified. Okay. So listen to that. So don't make duplication. Okay. So that we can save we need to respect the time of others also. Okay. Hope I'm clear. If your doubt is get clarified, someone is also asking the same doubt. Okay. I think you can lower your hand. Okay. Yeah. Now, what is the next topic that we need to consider? Intrinsic semiconductor. Okay. So we'll try to discuss about what? Intrinsic semiconductor. Intrinsic semiconductor. Please try to understand the basic definitions that I have given. Okay. Don't try to by heart it. Okay. If you understand the concept, you can easily remember either it is equation or the any definition that you can easily remember. But if you don't understand, even if you by heart it for 1,000 times, it's very difficult to remember. Okay. So try to understand the concept. And I'm explaining everything. Okay. Each and every point I'm considering and I'm explaining. Okay. So please try to concentrate. Now in this one, in this intrinsic semiconductor, what we are going to discuss, we'll see, and then we'll go for in detail. Okay. So we need to understand. We have given the last topic in the previous one is the wave particle duality. Yes, sir, that we have given. So here, two things that we need to consider. One is called bond model. Okay, that is what we have taken, and another one is what? Band model. Okay, or energy band model. This is what. So now what we are going to consider is bond model. Okay, so what I am considering is the bond model. So in this, what we are going to discuss is, we will try to identify what is a phonon, okay, photon, what is an electron, what is a hole. We'll see in detail. Okay, so try to understand what these points are going to be. Okay, we'll discuss about what? Phonons, photons, okay, free electron or electron you can call free electron, okay, and free electrons and holes. So starting with this we'll discuss. Okay, and then we'll see electron hole pair generation and recombination, EHP. Okay, this is going to be very brief. Later we are going to consider in detail. Okay, electron hole pair generation and recombination. Okay, yeah, here when I am explaining in a flow, okay, few things, okay, we are going to briefly discuss at one point of time. Later on we are going to discuss in detail. Okay, so please don't worry. Okay, try to follow the flow that I am giving. Okay, so electron hole pair generation and recombination, and then we'll try to discuss about concentration of electrons and holes, because this is very important for us. What it is? Concentration of electrons and holes. Clear? So these are the three things that we are going to consider in bond model, and later on we'll go for band model. Fine? Okay. Now, so what is our topic now? We need to discuss about phonons, photons. Okay, you can call it as electrons or free electrons also. Okay, anyhow, later on we are going to drop this word free. Okay, free electrons, and finally holes. Okay, now, yeah, please, what is the topic that we are considering now? This one, bond model. In that I am discussing. So try to follow that. Okay, so phonons, photons, free electrons and holes. Now I'll consider a silicon crystal. I'm taking example as a silicon material. You can consider it as the germanium also. Okay. So only the material parameters will be different. Otherwise, it is the same. Okay. So what I'm considering, silicon. Okay, crystal. Consider silicon crystal. Now, temperature matters now. Okay, silicon crystal at absolute 0 or 0 Kelvin, I can say. Okay, so here capital T represents absolute temperature. You know the relation, okay? And I think you know relation between, this is in Kelvin or degree Kelvin, I can say small t, which is in degree centigrade, plus 273, the basic relation. Okay, you know this. Okay, I'm considering the silicon crystal at 0 Kelvin. Okay, now let me represent the crystal structure here. Here for the convenience of drawing, okay, I'll represent like this crystal structure. Okay, try to follow this notation. Okay, yeah, please try to take the notes simultaneously. Okay, so this is nothing but two-dimensional representation of the crystal structure. What is this? 2D, two-dimensional representation. Okay, representation of crystal. Okay, crystal structure. So what this indicates is, suppose this intersection is there, no? Here I have a silicon atom and there are 4 covalent bonds, okay, with the adjacent atoms. Again, here there is a silicon, okay, there are 4 bonds. Here also that represents silicon, like that. Hope I am clear. I am taking for simplicity this type of representation for the crystal structure. Okay, so at this point I have a silicon atom. There are 4 covalent bonds surrounding this. Okay, instead of writing silicon and 2 bonds, I'm just simply representing like this. Hope I am clear. So I'll follow the same throughout the discussion. Okay, okay, fine. Now what is the condition here? What is the temperature that I am considering? 0 Kelvin. This is important. Yes. Now, can I write there is no thermal agitation? There is no thermal agitation. Okay, or there is no thermal energy, I can call, because it is at absolute 0. It is at absolute 0. If that is the case, we can very clearly see that no bond is going to be broken. Can I write like this? No bond, okay, is broken. Okay, nothing but, see, if you consider this is the silicon atom, you can see clearly that 4 bonds are completed. Here also 4 bonds are completed. Okay, or I can, same point, second, third one is also all atoms are bonded to, okay, 4 neighboring atoms. Yes or no? 4 nearest neighbors. Okay, 4 nearest neighbors. Okay, am I correct? Yes or no? Now, what is the nature of this intrinsic semiconductor material at absolute 0? Can you find any charge carriers here? Out of this 3, what we can say is there are no free carriers that are going to be present. Can I say yes? There are no free carriers. Yes or no? Simply we can conclude from these 3 points, there are no free carriers. Then what is the nature? What is the nature? It is insulator. Okay, so what we can say now, intrinsic semiconductor behaves like an insulator. Okay, but we must give the condition. Okay, it is not, you know, general statement. Okay, where we have considered at absolute zero. So intrinsic semiconductor behaves like an insulator at absolute zero. Please, when you are giving any statement, you must be very careful. Okay, here I'm talking about nature of intrinsic semiconductor at a particular temperature. What is the temperature here? Absolute zero, because I don't have any free carriers. Hope I am clear. Okay, now let us now consider the same silicon crystal, but I am going to change the temperature now. Okay, so now I am considering what? Silicon crystal. Okay, for T greater than 0 Kelvin now. Okay, I am increasing the temperature. Hope I am clear. I am increasing the temperature. Now what will happen? When you increase the temperature, there is a thermal energy. Okay, so because of that, the atoms are going to start vibrating with its mean position. Okay, I'm repeating this point. Once you make T greater than 0 Kelvin, there is a thermal energy. Because of this thermal energy, atoms start vibrating with its mean position. Okay, so if you remember the wave particle duality that we have given, phonon, what we have represented, it is the vibrating atom. So the first particle that we are getting here is what? Phonon. What it is? Phonon. Yes, okay. So once the atom starts vibrating with its mean position, okay, let me write that point. Each atom, okay, each atom starts vibrating with its mean position. Okay, with its or about with its or about the mean position. Okay, then what is this? Is nothing but what? A phonon. And what is the wave nature? Phonon is the particle nature. What is the wave nature? Elastic wave. Okay. Whenever an atom vibrates, whenever an atom vibrates, okay, so it generates an elastic wave. Okay, atom vibrates, it generates an elastic wave. Okay, and what is the particle duality for this elastic wave? Is nothing but the phonon. Okay, the corresponding particle nature is phonon. Okay, so this is how phonon is going to be present in the semiconductor material. Hope I am clear. Once you increase the temperature, atoms are going to start vibrating about their mean positions. This vibrating atom is nothing but what? Phonon. What is the corresponding wave nature? Elastic wave. Okay, so you must, okay, phonon is the particle nature, elastic wave is the wave nature. Hope I am clear. Okay, now these phonons, okay, are the, you know, what is that, elastic waves or waves are going to travel within the semiconductor material. Okay, now we'll see how we can get the photons. Please try to understand this point. We'll concentrate now on photons. Okay, now if you consider an atom, okay, let us take now at T equal to 0 Kelvin. Okay, at T equal to 0 Kelvin, what will happen? Suppose if this is the atom, there will be a nucleus which is positively charged, and surrounding this there are electrons which are revolving around the nucleus. Yes or no? Nucleus will have protons and neutrons. So positively charged, this is electrons. So this is the condition. Now when you go for T greater than 0 Kelvin, what will happen now? Okay. What will happen? T greater than 0 Kelvin, what will happen? Please try to concentrate. This point is very important. What we said, when T greater than 0, suppose, this is the atom. Okay. This is vibrating about its mean position. Okay. About its mean position, it is vibrating. Okay. Now when T equal to 0, we can very clearly see, okay, the effective center. Okay. I'll write here. In this case, effective centers of positive and negative charge is the same. Please try to understand this point. In this equilibrium, absolute zero condition, what it is? This is positive charge, no? And this is negative charge, which is revolving around the nucleus. So the effective centers you consider for positive as well as the negative, it is going to be the same. Am I correct? The effective centers for positive charge and negative charge. Positive charge means nucleus, negative charge is the electron cloud. Okay? But now T equal to 0, this is the atom position. Now it starts vibrating about its mean position. What will happen? Definitely, okay, there will be a displacement for the effective centers of positive and negative charge. Okay, so please try to understand this point. This is very important. Okay, now when T is greater than 0, okay, what will happen now? The effective centers, okay, let us take center of positive charge. Okay, nothing but what? Nucleus. Okay, and negative charge. Okay, negative, I can say positive point charge, negative point charge, cloud, electron cloud. Hope I am clear. Negative point charge, which is the electron cloud, is different or is separated by a small distance. So this point is very important. T equal to 0 Kelvin, this is the position of the atom. You can say very clearly that the effective centers of the positive charge and the electrons which are revolving around this are going to be the same. Now this, when it starts vibrating, there is a separation between the effective centers of positive and negative charges. Okay, so what I am getting now? What is this structure now? Let us take, this is minus, this is plus. So what is this? It is called electric dipole. It is nothing but what? Electric dipole. Yes or no? It's nothing but what? Electric dipole. Actually, it's a vibrating atom. So, a vibrating atom can be considered as what? Oscillating electric dipole. Okay, please again try to understand this point. Okay, I'll write that. This is important one. A vibrating atom. Okay, can be considered as what? An oscillating electric dipole. As an oscillating electric dipole. So what you will get from an oscillating electric dipole? If you remember your antennas, what it is? It's going to be the electromagnetic wave. Okay, so oscillating electric dipole, which is the source of what? EM wave, electromagnetic wave, and corresponding particle nature. Corresponding particle nature is what? Photon. Hope I am clear. The corresponding particle nature for the electromagnetic wave is nothing but what? Yes, photon. Hope I am clear. So this point is very important. Please try to concentrate and understand this. Okay, so what it is, when you increase temperature, the atom starts vibrating about its main position, okay, which creates, or because of that there is a displacement from the effective centers of negative and positive charge. And what is that? Is nothing but called as the electric dipole. Okay, so a vibrating atom can be considered as what? An oscillating electric dipole, which is the source for obviously electromagnetic wave. And what is the corresponding particle nature? Photon. Hope I am clear. This is how we can get. Okay, now let us go for next particle. What it is? Free electron. Okay, it is nothing but what? Free electron. Okay, now what will happen? We said two particles are there. No, one is the phonon, another one is the photon. Or in terms of waves, if I talk, it is the elastic wave here. And what about this? It is the, here wave nature is EM wave, particle nature is photon. Yes. Now if I consider as a particle, then what will happen is they can converge to a particular point. I'm giving only one or two here, but there will be many. Okay, so particles, in terms of particles, if I say, they are going to converge. Okay, if I'm talking with respect to particles, then they can converge. Okay, they can converge to a particular point. Okay, particular point. Or same thing if I talk about wave, with respect to waves, okay, they can interfere. They can interfere particular point. Please try to follow the terminology that we are using. If I am considering it as a particle, I am talking what? Converging. If it is a wave, I am talking about interfere. Okay, maybe the effect is going to be the same, but you must understand the terminology that we are using. Okay, fine. Yes. Now if that is the case, what will happen? Suppose the number of particles are converging to a point, or a number of waves are interfering at a particular point, and the energy of the total particles or the waves is same as the energy gap, then that particular covalent bond can be broken. Yes, I'm clear. Okay, so let me write that point. If the total energy of the particles that are converging, okay, that are converging, are waves that are interfering, waves that are interfering is equal to the covalent bond strength, or simply bond strength. Okay, then that particular covalent bond is broken. Okay, now in case of silicon, it is how much? Yeah, if we are not mentioning anything about the temperature, default it is at room temperature. So what is it? It is 1.1 1 electron volts. Okay, so it is 1.1 electron volts. Okay, and for germanium it is 0.72 electron volts. Hope I am clear with this. Okay, when the particles are converging or the waves are interfering and the total energy of them, okay, either you talk about with respect to the particles or with respect to the waves, it is equal to the what? Covalent bond strength, then that particular covalent bond is going to be broken. Okay, now let me represent that in the whatever the representation that we have given now. Let me write that. Please try to understand. Okay, so this is the two-dimensional representation of the crystal structure that we are following now. The same thing I am giving here. Okay, now for example, let us consider at this particular point, okay, the particles are converged, the waves are interfered. Because of that, this bond is broken. Okay, now this is not complete. So because of this, what will happen? There is a free electron that is going to be generated. We'll call this as free electron. Anyhow, later on we are going to drop this word free. This is electron. And there is a vacancy here, okay, or incomplete bond. I can call it as what? Vacancy or incomplete bond. What is it is going to be? It is called as the hole. Okay, let me write it is hole. Am I clear? Okay, so here I have taken one bond, but it can happen many ways. No, there are not only one or two particles, there will be many particles, and this convergence can happen at different points. Because of that, there will be what? Electron hole pairs are going to be generated. Hope I am clear with what I have written now. Yes. Okay, so this is how free electron we are going to get. Now let us further consider this hole, and we'll try to understand. This is very important one now. Okay, hope I am clear. Let us go for the next particle. What we are going to consider? Concept of hole. Concept of hole. Please concentrate, because many of you may have doubt how this hole is going to exist, and how the hole is going to have the positive charge and how it is going to respond to the applied electric field and all. Will another 10 minutes, you can get clarified many doubts. Okay, please concentrate. Okay, now let us consider the same crystal structure that we are going to draw now. Okay, let me draw one more time. Okay, please try to concentrate. Now what we have taken, let us take, this is the incomplete bond. Okay, and here, okay, so because of this I have a free electron. Okay, and this we are calling it as what? Hole. This part we are calling it as the hole. Okay, now suppose, please try to concentrate, this point is very important. Now if I want to make a bound electron, see all these electrons which are present here, we are calling them as the bound electrons. There are two terms which you must understand. One is, okay, let me write here, one is bound electron. Okay, bound electron, and another one is what? Free electron. Now out of this, which is responsible for the current? Free electron, not the bound electron. So here I have, for example, I have taken here, okay, so one free electron is present, but what about the electron that is going to be present here for the bond? It is going to be bound. So one electron is for this silicon atom, another one is for this silicon atom. Total two bound electrons are present here. Hope I am clear. Okay, so you must understand what is bound electron, what is free electron here. Okay, because we have not considered still what is the valence band and conduction band. For this purpose, you understand what is bound electron and what is free electron. Hope I am clear. Okay, now if I want to make a bound electron as free electron, how much energy required? the bond strength. That is what we have given in the previous page. No, if I want to break a covalent bond so that electron hole pairs are going to be generated, I need how much of energy? Bond strength. Okay, so please try to understand this point. If we want to make a bound electron as free electron, okay, the amount of energy required is the amount of energy required is what? Is bond strength. Is nothing but what? Bond strength. Hope I am clear with what I have written now. Okay. If I want to make a bound electron as free electron, how much energy required? The bond strength energy. Okay, but see, once whatever we are considering here, T greater than 0, it is obvious. Please remember it. Okay, it is default that we are considering the temperature greater than 0 Kelvin or default at room temperature. Now, with that thermal energy, the adjacent electrons adjacent bound electron that is present here will always try to move into this vacant position. Now we are using one more here. What is that? Vacant position. Try to understand this also. What it is? Vacant position. Call it as broken bond. Is nothing but what? Broken bond. Okay. Now, if I want to move this, bound electron into this vacant position, it is not required that this much of energy. Even the thermal energy is sufficient so that this bound electron will always try to move into this vacant position. So then what is the, where the vacant position is present now? Let me draw. Please try to understand. This is very important one. Please concentrate. Okay. Yeah, we have 5. Okay. So here, initially where the vacant position is this one. This is the vacant position. Okay. Initially. Okay. Now what I am going to do, it is nothing. We are not supposed to, we are not applying any external energy, but the temperature is going to be greater than 0 Kelvin itself. So there is a thermal energy now. T is greater than 0 Kelvin. There is a thermal energy. What will happen? This, okay, let us consider this one. Okay, this bound electron is moving to this position. Okay, now this must be what? Complete bond. Okay, and this is incomplete bond. Please try to understand. Okay, now this is electron. Yes or no? This is, here I am having the free electron, or sorry. Okay, now this is nothing but what? This is nothing but what? Hole. Yes or no? This part is nothing but what? Hole. Now free electron is moving from here to here, but hole is moving in the opposite direction. Hope I am clear? Yes. Bound electron is moving in this direction here. Now what about the hole? It is moving in the opposite direction to your bound electron. Am I correct? Yes. Okay. So like this. Now again, this adjacent, bound electrons are there. No, they will always try to move into this vacant position always because of the thermal energy. Okay. Hope I am clear. Okay. Now let us consider. Okay, I am applying some field for the semiconductor material. Okay, so let us take, this is the semiconductor. Please try to understand this point. Concentrate. This is what? The semiconductor that I am going to consider. Okay, now for this I am applying some field. Okay, let us consider. Okay, applied voltage, there will be an electric field that is going to be present, because this is plus and this is minus. So this is the direction of the electric field. Yes, this is the direction of the electric field. Okay, now this electric field will exert force on the charged particles. What is the force? F is equal to what? Q times of applied electric field. Anyhow, now how the free electrons will move here? Please try to concentrate. How the free electrons will move? Opposite to this electric field, because Q is minus. So free electrons are moving in this direction. Okay, free electrons. Okay, now if you consider this along with free electrons, now there is a movement of bound electrons also, no? Yes or no? Because even if thermal energy or you are giving the external excitation, with that also these electrons are going to move. I think you are following. Okay, now there are bound electrons going to move in which direction? I am considering the bound electrons. In which direction these bound electrons are going to move? Obviously, again apply this F equal to Q times of, they are going to move in the opposite direction to your applied electric field. Now they are also moving in this way. Hope I am clear. Okay, now please, this scenario will change it now. Okay, for our convenience we'll change that. Okay, now the same semiconductor material I am considering, I am applying the voltage V here. Okay, yeah, anyhow, because of that there is a current that can flow. Okay, now for us there is no confusion with respect to free electrons. So I can simply write like this: free electrons are moving in this way. Is it fine? Now in terms of, in place of bound electrons, what I can write now, you can very clearly see here, this red arrow mark indicates movement of what? Bound electron. But what about the hole? Initially hole is present here. Now this is located to this position. Now hole has been moved. Okay, from where to where? Hole has been moved in this direction. Yes or no? So this is what? Movement of hole. And this one, this arrow mark indicates movement of electron. Movement of not simple electron, bound electron. Bound electron. Am I correct? Yes. So if you consider these two, you can very clearly see that this hole is moving opposite to the direction of the bound electron. So can I replace it now? Now this is the direction of what? Hole. Okay. Are you understanding? Okay. And that is the reason why we are considering hole as the positive charge, because electron is negatively charged. We know very clearly that electron is negatively charged, and this is the reason why we are taking hole which is having what? Positive charge. So hope I am clear with what I have explained. Please concentrate. I'll give one more time this one. Okay. So what we are considering here is, we are discussing about the concept of hole. Once the electron hole pair has been generated, so you need to understand bound electron, free electron, vacant position or the broken bond. Okay. So this is nothing but the broken bond or incomplete bond hole, and which is moving out of this, we are calling it as free electron. This free electron is responsible for the current, not the bound electron. Now all other, you can very clearly see there are many number of bound electrons. There are large number of bound electrons. Let me write that point. Okay. There are large number of what? Bound electrons. Large number of bound electrons. Okay, and few vacancies. Few vacancies. This point is very important. There are large number of bound electrons and very few vacancies that are going to be present. Okay. Now, the bound electron, please try to understand, the bound electron will move, okay, via the vacancies that are present in the crystal structure. Is this point clear? These two, please, you have to understand these two. There are large number of vacancies that are, large number of bound electrons that are present, but there are very few vacancies, and the bound electron will move via the vacancies that are present in the crystal structure. Okay. Now, if we want to make a bound electron as free electron, the amount of energy required is what? Bond strength. But to move a bound electron into vacant position, okay, the energy required is going to be very minimum. That also I'll write. To move a bound electron into vacant position, much of the energy is not required. Much of the energy is not required. Yeah. Please try to understand these points. If I want to break a covalent bond and generate a free electron, bond strength of amount is required. But what about to move the bound electron into vacant position? Much of the energy is not required. Clearly see, there are large number of bound electrons and very few vacancies, and the bound electron is going to move via the vacancies that are present in the crystal structure. Okay. And with respect to the applied electric field, this is how the free electrons, bound electrons are going to respond. Okay. Based on the very basic relation. Okay. From that we are giving Q is going to be minus, that's why it is opposite. But instead of bound electrons, we are taking it as the whole. Okay. So the actual scenario which is happening when you apply the electric field is the bound electrons are moving via the vacancies, but we may not be in a position to represent. For our convenient way of representation, we are calling it as what? Hole. So we can very clearly see from this, okay, the bound electron moment and the hole moment, they are in the opposite direction, and that is the reason why I am taking hole as the positive charge. Yeah, I hope I am very much clear with what I have explained now. This is very important because we have the doubt how the hole is going to exist, okay, and how hole is going to be positive charge. Hope I have clarified that particular doubt. Okay. Now another 2 minutes, we'll about to close. Okay. Here what we need to understand is, if you see the mobility of electron and the mobility of the hole, okay, we say mobility of the hole is less than the mobility of the electron. Okay, we'll try to understand why. Okay. Yes. Now let us consider the movement of free electrons and the bound electrons. Let me write first and then I'll explain. The movement of bound electrons, okay, bound electrons in response to the electric field that we are applying, okay, electric field, okay, will definitely be different than the movement of free electrons, free electrons. So we can very clearly understand that the free electrons tend to move faster compared to bound electrons. Okay, compared to bound electrons. Yeah, if you you just apply your common sense, we can very clearly see that. Yes or no? Yes, the movement of bound electrons in response or with respect to the electric field that you are applying is going to be different than the free electrons. Okay, and nothing but what? Free electrons can move faster than the bound electrons. Please try to understand. Okay, that is the reason why the mobility of electron is more than the mobility of the hole. Okay, so here we'll try to understand one simple topic called as the effective mass. Okay, with this we'll close. Effective mass. Okay, let us indicate with M. Okay, so the effective mass is equal to some constant, okay, into actual mass. Okay, effective mass is nothing but what? Some constant into actual mass. So let us indicate this is M is equal to, okay, and there will be a some constant which we can get it into M naught. Okay, so how you can get this M naught is nothing but mass in vacuum. Actual mass is nothing but what? Mass in vacuum. Mass in vacuum. So how you can calculate this effective mass? Yes, how you can calculate effective mass? M is equal to applied force by gain in the acceleration. So F is what? Applied force. Okay, applied force, and A is acceleration gain. Okay, what it is? Acceleration gained. What is the meaning of this? You say you take a particular particle in vacuum, apply certain force, calculate how much acceleration it got, then take the ratio that will give M naught. Now the same particle, you keep it in a particular medium, apply the same force, measure how much acceleration it got, take the ratio that will give the effective mass. Hope I am clear? Yes, effective mass is some constant into actual mass. Actual mass is nothing but what? Mass in particular mass in vacuum. Effective mass is in a particular medium you are measuring. How you can get it? Using this relation. M is equal to what? F by A. F is the force up, that is you are applying. So M naught, how you can obtain? Keep the particle in a free space, apply certain force, calculate or measure the acceleration that it is obtained. Now take the same particle, put it in some other medium, apply the same force, calculate or measure the acceleration that is gained. Okay, that is what we are going to get. Okay, now we can represent, yeah, Mn, okay, is the effective mass of electron. Okay, effective mass of electron. MP is going to be effective mass of hole. Okay, so yeah, again this notation is our convenient way of representation. In some textbooks, Mn MP they will take it as actual masses, then Mn star MP star as the effective masses. It depends. Okay, so I am following Mn MP as the effective masses. Okay, now with the discussion that we made here, we can very clearly see the effective mass of electron is going to be less than the effective mass of the hole, because your electron can move faster. Yes or no? It can move faster. Yes, bound electron, sorry, free electron can move faster than the bound electron. Okay, so we can conclude from this what? the effective mass of electron is less than the effective mass of hole. And here the important point, I am talking with respect to what? Electrical conductivity here. With respect to that, this parameter, Mn is going to be less than Mp. Effective mass of electron is less than effective mass of hole. I think I'm very much clear. This part is very important. Okay, the concept of the hole that I have explained, how it is responding to the applied electric field, and from that the conclusions that we made. Okay. Yes. Yeah. Please. When you are asking the doubts, if there is any repetitions, okay, don't make repetitions. Okay, if you are doubt someone is asking the same doubt, okay, please lower your hand. Okay, so don't waste our time. Okay, some of you are not responding. You are raising the hand and you are not responding. Okay, so we'll try to respond quickly. Okay. Yeah. Rajita, please ask your doubt. Rajita?
Hello?
Yeah. Yes, please. Can you able to hear me?
Hello, sir.
Yeah, please go ahead. Hello?
Hello, sir. Am I audible?
Yes, go ahead. Ask the doubt.
Sir, once will you able to explain the topic of that bounded electron, sir? I was confused with that.
Which one? Give the page number.
Page number 19F.
Okay. What is your doubt here?
Sir, you were saying that whole. You have mentioned the direction of free electrons moving outside and bound electrons is coming inside. Means they are.
Come again. Please come again. What you said? Movement of
free electrons towards outside.
No, it is not. To represent it as a free electron, your electron will not come out of the crystal structure. Please remember, it is there in the crystal. It can move freely. It is not bound to any atom now. That is what the free electron means. It is not coming out of the crystal structure. Please.
Okay, sir. Then the whole. Okay, sir. I got it. Okay.
Yeah.
Okay. Thank you, sir.
Yeah. Sagar, please go ahead. Sagar.
Hello.
Yeah. Your voice is.
Hello. Can you hear me?
Yes. Go ahead now.
Okay. Sir, I have two doubts.
Yeah.
Sir, you said that free electrons as a particles, they converge to a particular point. Sir, what is the meaning of that?
See, when your electron is moving, it is not in like, it's there are many things that are going to be present in the crystal structure. No, it cannot move very freely wherever it wants. There will be some collisions.
Okay.
Yes or no?
Okay.
That collision point is nothing but convergence point.
Okay.
Yeah. When it.
Okay. So, but sir, I thought that means like charges so repel each other. So how can they converge?
I'm not getting like charges. Yeah, obviously.
So I got confused in that.
See. No, I am not saying only electrons are converging.
So how can they converge?
Hold on you.
Okay.
I am not saying that only electrons are converging to a particular point. Okay. You are only thinking there is only one electron, but there are many things that are going to be present in the crystal. No, you have to consider the overall effect. Overall effect you have to consider. You are thinking only that there are only electrons. No, there are many particles, many atoms, many things that are going to be present in the crystal structure. So there is a possibility of converging different particles into one particular point. Fine. Hello. Okay. Yeah, please. Who is this HP? Please go ahead.
Hello. Yes, sir.
Yes.
Sir, I have a doubt that you told bounded electrons are responsible for means they are like holes.
I'm not getting your come again. What are the statement that you have given?
Sir, you told bounded electrons are means the bounded electrons are holes. The moment of bounded electrons
bounded electrons are not holes. Bounded electrons movement and hole moment, they are going to be in the opposite direction. Please be careful. I have not mentioned that bound electron is going to be hole. Bound electron is different, hole is different.
Sir, but the moment of bounded electron
moment is different.
Means they are opposite to the moment of holes. You are telling that, sir.
Obviously, I have very clearly explained, no?
But sir, the holes are responsible for current, and you told that bounded electrons are not responsible for current, sir.
Yes.
That means,
see, here you need to understand one important point. There are many number of bound electrons now.
Yes, sir.
Out of which, how many are moving to the vacant position? Very few. Only those bound electrons are going to be responsible. I cannot generalize that bound electrons are going to be responsible for current, but hole is responsible.
Yes, sir. Means the bounded electrons which are moving towards that vacant position.
That you can take.
Are
but
responsible for,
yes, that is correct. But you are not supposed to generalize. Bound electrons, I cannot say they are going to be corresponding for the current. But
sir, but I have another doubt. Means how that bound electrons will means comprise to that hole. Means there are very numbers of bounded electrons. Then which bounded electrons will move towards that hole?
Very adjacent to that, they will move always. And if they have sufficient, come and occupy that. And in that process, not only bound electrons, see, this free electron also can occupy this vacant position.
Okay, sir.
Okay, that process we'll call it as recombination. Anyhow, that we are going to discuss later.
Okay, sir.
Fine?
Yes.
Yeah. Snigdha, please go ahead. Snigdha?
Hello?
Yeah.
Yes, sir. You said that a vibrating atom generates a phonon. And you also
vibrating
said
atom itself is a phonon.
Okay, yeah, vibrating atom itself is a phonon.
Fine.
And you also said that it is a vibrating atom is considered as an oscillating dipole.
Obviously.
So will phonon and photon be created at the same time?
It can be.
Okay.
It can be.
Or will the frequency of oscillation depend on which particle is created?
That's going to be different then. I think it is not required for us to go into that, frequency and all. It's a different issue.
Okay.
I'm not going to touch those.
Okay, but it is possible that both particles can be created at the same time?
Yes, possible.
Okay.
Okay. But how far we cannot assure it. Okay.
Okay. Thank you, sir.
Yeah. Yeah, who is this 121810401? Please go ahead. Please respond fast. Prabhakar, please ask your doubt. Prabhakar. Shavanti, please. Shavanti. Yeah, Prajakta.
Yes, sir.
Yeah, please.
Sir, how do we decide which bounded electron is going to occupy the whole position?
Why we are not supposed we are not in a position to decide, but mostly the adjacent bound electrons are there. Now, suppose you consider this. Adjacent to this, there are some bound electrons. No, most of the times they will try to occupy. But for bound electron, it has the sufficient energy. Maybe from longer distance also it can come and occupy. The important point is which bound electron is coming and occupy is not the not that much important for us. But whether bound electrons are moving into the vacant position or not, that is important, because which corresponds to the current. When bound electron is moving into the vacant position, nothing but hole is moving for in our representation, which results in a current. So whether there is a movement or not, that is most important for us rather than which is moving.
Sir, but as bounded electron is moving in the becoming free electron, then it is moving from
No,
stable.
no. Bound electron is not bound electron. Come again. Come again.
Then
The question.
then it is going from stable state to unstable state, and how that can be possible?
Where is stable? Which you are calling it a stable state and which is
The
unstable?
bounded electron is stable, no?
That's why no. It's not going to be. Suppose one bound electron is moving to the vacant position. It will not stay there. Then it will go, because you are saying no, it is unstable state. That vacant position is creating some disturbance in the crystal, which is an unstable state. No, so it's going to be a continuous process.
Okay, sir.
So don't think that once one bound electron is entering into the vacant, it is going to stuck up there. No.
So this is continuous process.
Obviously, but you must ensure that T is greater than 0 Kelvin.
Okay, sir.
Fine. Yeah, Shreya, please go ahead. Shreya. Shreya, please. Yeah, your voice is not, there is no clarity. I'm not getting your voice. Shreya, your voice is not, clear. I am not able to hear. Okay. Harsha, please. Harsha.
Hello.
Yeah.
Sir, am I audible?
Yes, go ahead.
Sir, for suppose if there are two vacant spaces available, that means two holes, and there is a possibility of this bonded electrons to occupy, no, sir?
Same. How they can occupy?
So if these two
See,
holes
what is here bound vacant position means one covalent bond has been broken. Yes. So only one electron can come and occupy. How come two? They will decide, okay, depending upon the energy, and there are many other factors. Only one is going to occupy.
I'm assuming that if there are two holes present, like two bonds are broken.
Not okay.
And if two vacant, if two bounded electrons occupies those spaces, and if now the electron loses its energy, and if it comes back to occupy the hole, will the electron occupy, or will the same?
No, that process, that is what I am calling. No, it is called as recombination. Please, there are two different things. If free electron is coming from the free electron is occupying the vacant position, we will call it as the recombination process.
Yes, sir. Okay. That one I got it, sir. But I'm saying that if the vacant position is occupied by the bounded electron,
fine.
And now if the electron loses its energy,
how it is going to lose its energy? Bound electron is when it is moving within the same band, no. If it is coming,
free electron loses energy.
Fine.
And so it needs some vacant space to occupy, no, sir?
Definitely will be there. See here, I have given only one or two, points where there are vacant positions. You just assume how many number of, suppose you take the silicon crystal, what is the atomic density of silicon? It is 5 into 10 power 22 per centimeter cube. That is per unit centimeter cube volume. If you consider, there are 5 into 10 power 22 atoms are present, out of which what I have represented here, only one.
Okay.
Are you getting?
Yes, sir.
Yeah. Okay. Krishna, please go ahead. Yeah, please respond fast.
Hello, sir.
Yeah.
Sir, page 17F.
17F. Fine. Yeah.
So here will only the nucleus move, or both electron and nucleus move together, sir, when they are vibrating?
See, about its main position, I have said no. Nucleus will not move. How nucleus will move?
So only electron.
Around. What about electrons that are revolving around the nucleus? Definitely there will be a displacement, no?
So because only electrons will be displaced.
See the vibrating atom about its moon position. See the, suppose this is equilibrium. Sorry, at t equal to 0. Now it starts vibrating about its mean position. See the nucleus. Nucleus is changing.
No.
But what about the top and bottom tips?
Acha, it is changing.
Yeah, that is nothing but actually electrons are revolving around it, no? So you can take it in that way.
Sir, and so is a combination of positive and negative charge together lead to photon, sir? Is together called as photon?
No, see, don't give statements like that. I have very clearly mentioned. See the is a dipole. Negative
dipole.
and positive charge separated by a small distance. Then you can call it as electric dipole. And this electric dipole, if it is oscillating, it is going to generate the electromagnetic wave. And what is the corresponding particle nature? Photon.
Okay.
Got it?
Yes, sir. So in page 20F, how bounded electron flows in the direction of the same as free electron, sir? That I didn't understand.
Bound electron?
How the direction of both bound and free electrons are same, sir?
What is the charge of free electron or bound electron?
Both are negative.
How they will respond with respect to the applied electric field?
So opposite to the direction of the field. Okay.
Yeah.
Yes.
Fine.
Sir. Yes. Thank you, sir. Thank you.
Yeah. Yeah, Harris, please go ahead. Harris.
Good afternoon, sir.
Very good afternoon.
Sir, if a bond is broken inside the crystal of the silicon, how many electrons are going to be created?
Only one.
Only one.
Only one bond is broken. Only one bond is broken.
Yeah, but the involvement in a bond, there are two electrons which are involved. So, like, how is it going to be decided? Like, from which silicon atom the electron is going
Why
to be
you need to decide, man? Why you?
Sir, maybe.
Is there any what I'm asking is, if you decide from this silicon is electron is released, is there any effect? We are considering as a whole how many number of electrons and holes are going to be generated. That is our interest.
Okay, all right.
Now it doesn't matter which silicon atom is breaking the covalent bond and releasing the free electron for us. Maybe if you go for for your specializations like that, then it's going to be matter for you.
All right.
Yeah. Okay.
Okay, and one more doubt, sir, regarding the vibration of the dipole. You said no, sir. Can you please explain that again? Explain it. How
I have explained now itself. I have explained. No, are you not there?
Yeah, I was listening.
You have not got that point. Okay, fine. See, this is a T equal to 0 Kelvin.
Yeah.
Okay. Now, when you increase the temperature, there is a thermal energy. This atom starts vibrating about its mean position. Now, the fingers that I am holding, it is a nucleus. You consider that the top and bottom of the tips, okay, and one part of your electron cloud that is moving, okay. Circularly, they are moving, no. Now, can you see there is a displacement of effective centers of positive and negative charge? Yes.
Yes, sir.
That is what I have explained.
All right. Thank you so much.
Yeah. Chandra, please go ahead. Chandra.
Yes, sir.
Yeah, please.
Sir, 18F, sir. Page number.
Page number?
18F.
Fine.
Sir, if the total energy, that read sentence, please explain also.
Total?
That sentence, sir, if the total energy of the particles that are converted.
I want to explain that.
Yes, sir. If it is equal, then the bond gets broken, sir.
Obviously. See, particles are converging to a particular point, and all, suppose there are, for example, I am taking 10 power, 10 particles are converging to a particular point, and take the energy, total energy, anyhow that we are going to discuss in the next class. Total energy is same as the bond strength. Obviously, the bond strength is going to be broken.
Okay, sir. Sir, if temperature exceeds also, bond breaks, no, sir.
Temperature exceeds means what?
More than
if thermal energy is itself is enough to break the covalent bond, yeah, it will be, obviously.
Okay.
Okay.
Okay. Thanks.
Yeah. Yeah, 91816.
Am I audible?
Yes,
Sir?
yes. Yeah, please.
Sir, I have doubt in the page 19F.
Fine.
Sir, in this you have said that in order to make a bound electron as free electron, the energy required is bond strength. And what if the energy required is greater than the energy gap of the valence band and conduction band?
I'm not getting your question, please. Please come again.
Sir, you said that
yeah,
in order
energy
to
make the bound electron to free electron, bond strength is required. Fine. Then what is your doubt?
But what if energy required is greater than the energy gap in the semiconductor?
What is the energy required greater than energy gap? Means what?
Yes. Means sir, in the case of semiconductors, if we like give energy greater than energy gap, then also this can happen, sir. This
Obviously, I have given whatever bond strength more than that. Obviously, if you can able to break the covalent bond with bond strength more than that, obviously you will break it. No.
Okay. So sir, is the like energy gap and the bond strength two different things?
Yeah, still I didn't came to energy gap. No, that's what if you see the semiconductor, we have very clearly mentioned bond model, band model. Still I'm sticking to the bond. Let us talk about only bond model.
Okay, sir.
Yeah. Shivanaik, please make it fast.
Right, sir. So in photon and phonon, you have given that vibrating atom will produce phonon and vibrating atom will produce photon.
Not you cannot say produce, but the overall effect can be considered in that way.
That means if while after vibrating atom, if it produces an elastic wave, it is a phonon, and if it produces an EM wave, it is photon. That's all right, sir.
Yeah.
Sir, and coming to this free electron case, you said that the waves when interfere, it acts as at a particular point, it produces a free electron. So these waves are nothing but these electron, these EM waves and
yeah, obviously no. That is what waves in the sense what waves you are going to have elastic wave and.
That means can we say that phonon and photon will be able to produce this electron, free electron?
Yes. That is what I said no very clearly. Particle nature, if you talk, it is with respect to what phonon and photon. If you talk about wave nature, it's elastic and EM wave.
Okay, sir, fine. So, but one last doubt. You have given the statement, no, sir. A mass of electron is less than mass of a hole.
Not mass, effective mass, please.
So, okay, effective mass. Sir, this thing I did not get, sir, actually.
What is that, man? See, do you understand the moment of bound electron and free electron is going to be different?
Yes, sir.
Got it? Now, obviously, your free electron can move faster than bound electron means what is the effective mass? You just apply to this, how you are calculating the effective mass, applied force divided by the acceleration, no?
Okay.
You just analyze from that. Which one is going to have higher acceleration? You just identify from that. Or simply, you just use your common sense. If it is moving faster, okay, obviously its mass is going to be less only, no?
Yes. So with that, how we consider with the how we relate to holes? That I got confused actually.
No, I'm not getting your question.
Okay, because we know that a mass of free electrons is very less compared to the bound electrons.
No, not in that way. Okay, bound electrons here, we are taking the moment of bound electrons and holes we are taking.
Yeah. Okay.
I'm not getting your doubt.
Oh, okay.
Where you are not. You just spend some time, okay, by taking this equation, no, effective mass equal to force by acceleration, you can get it.
Okay.
Fine.
Okay, sir. Thank you.
Yeah. Pawan Sharma, please go ahead.
Good afternoon, sir.
Yeah, very good afternoon.
Sir, you told that the holes and the bonded electrons direction is opposite direction. So, but how can we say that it is completely in opposite? Because if sometimes the bonded electrons present in the
how we can say, man, I have explained very clearly, no?
So,
have you not listened that?
No, sir. I'm just saying is that whenever the bonded electron has been moved to some other vacancy place, then the hole is generated.
Then hole is not generated. Please. Hold on. Generation is if you break a covalent bond, then electron hole pair is generated. Here, when bound electron is moving from one position to the vacant position, you are not generating the hole. Okay, you are just moving. There is a lot of different generation and movement. Is it clear?
Okay, sir.
Sir,
fine. And one more doubt, sir. Whenever this bonded electron is moving through this crystal space, will it be influenced by other electrons?
Come again, come again.
Whenever this bonded electron is moving into this vacancy place, will it be influenced by any other electrical charges?
Obviously, because there one electron and one vacancy, there are many things that are going to be present. Overall system effect you have to consider. Okay, crystal structure is not simple as that. You have to.
Yes, sir. And you have explained two figures about this motion of free electrons on the applied electrical field, sir. And you have told in second figure about the hole direction, sir. And can we consider about hole pairs, or electron hole pairs, that hole pairs?
Electron hole pairs?
Are these holes because are these holes only because of bonded electrons, or are these holes?
No. Please. You try to understand what is hole here. I am calling. When you break a covalent bond, okay. When you break a covalent bond, one free electron has been released, and there is a vacancy. That vacancy is the hole. Please, that vacancy is the hole. And how this hole is moving? Actual scenario is bound electrons are moving. Actually. Okay, physically you see bound electrons are moving, but that we are not in a position to represent. Yes, can you represent that? Instead of that, what you are taking is the vacant position is moving in the opposite direction, and that we are taking it as the whole, and that we are representing it as a positive charge. Clear?
Thank you, sir.
Yeah.
Thank you, sir.
Yeah. Sai Charan.
I got a doubt, sir. Page 19.
Yes.
There you have written to move a bounded electron into vacant position.
There is a lot of disturbance from your side.
There is written to move a bounded electron into vacant position. Much of the energy is not required to.
Yes.
A bounded electron to move towards a hole, the covalent bond needs to be broken there, no, sir, for the bounded electron to come into the hole.
But you are not, here new bond is not broken. No, already one bond is broken, and it is creating some disturbance in the system. So always the adjacent electrons will try to occupy and settle down there.
Yes, sir. That bounded electron to form a electron hole.
I got your doubt. 1 second. Suppose there are 10 covalent bonds are broken. For example, you take at a particular point 10 covalent bonds are broken. Now, if one bound electron is moving into the vacant position, how many number of covalent bonds are broken?
Only one, sir.
No. See, try to understand my question. At a particular instant of time, 10 covalent bonds are broken. Okay. As a whole, consider. Now, if one bound electron is moving into the vacant position, what is the total number of covalent bonds that are broken in the crystal structure?
10, sir.
10 only, yeah. Where you require energy now? You need to consider as a whole, not a simple one. Okay.
Yes, sir.
Got it? Nitish Kumar.
Hello, good afternoon, sir.
Very good afternoon.
Sir, I didn't understand the concept of effective mass.
Concept of?
Effective mass.
Yeah, what you are not in a position to understand, tell me.
So what is the constant, sir?
What is the?
Constant.
Yeah, it depends on the medium.
Okay, sir.
It depends on the medium, okay? For different mediums, actual mass is going to be the same, okay?
Yes, sir.
Actual mass will be the same, but effective mass, there will be some factor which you have to multiply. That is what constant is going to be.
It's the internal force, sir?
No. See, okay, I'll tell you. See, the m naught you know anyhow.
Yes, sir.
Is at a certain medium, you find out the effective mass. What is this constant now? Effective mass divided by the actual mass.
Okay, sir.
Fine?
Yes, sir.
Jnana Meghana, please go ahead. Yes, Jnana Meghana. Kalyan Kumar. Kalyan Kumar.
Hello, sir.
Yeah, please.
Good afternoon, sir.
Very
I
good
have
afternoon.
a doubt in page number 17F, sir.
17F. Okay.
Sir, here, what is the effective centers mean, sir?
What is center? For positive charge, there will be a center, no?
Yes.
And negative charge also will have the center.
Yes, sir. But how can you say that effective centers will be same, sir? At
Yeah.
temperature?
When you consider this, is this atom is is there any moment for nucleus as well as the electron?
No,
Anyhow,
sir.
electron will revolve, but as a whole, if you consider what is the center, effective center, is it changing?
No, sir.
Same. That's what I have written. No, effective centers of positive and negative charges are the same.
Yes, sir. Sir, I have another doubt, sir.
Hmm?
The concept of hole, sir.
Fine. Tell me.
19F.
19F.
Sir, here, when a hole is created, bounded electron is going to occupy the vacancy, no, sir?
Yes.
So there is a presence of hole at the bounded electron place, no, sir, again.
Obviously.
Sir, then what is the use of filling this vacancy, sir? Also, there.
No, I am not filling, man. I am not filling. It is going to be a continuous process. See, when you create some disturbance, always there is a tendency that nearby the vacant position, the nearby bound electrons will always try to move into that vacant position.
Yes, sir.
What is the use means? Now there is a movement of charge carriers. No, here actually bound electron is moving.
Yes, sir.
What it results? Current.
Yes, sir.
That is the use.
Sir, previously one of the students has asked a doubt now, sir. The energy required for the bound electron to break the bond. I didn't understand that doubt, sir. Can you explain me that?
See, almost 15 people has been asked that doubt, man. How I can? What is your doubt? Tell me. I can clarify. Others' doubt, how I can clarify?
You have said that point, no, sir. To move a bound electron into vacancy, much energy is not required.
Obviously.
But you have to break the covalent bond from.
Why you need to break? That is the reason I am telling, man. If suppose at a particular point of time in the crystal structure, 10 covalent bonds has been broken. Okay.
Yes, sir.
Now there is no extra covalent bonds that are going to be broken. Okay, I am considering. Now one bound electron has been moved into the vacant position. What are the total number of covalent bonds that are broken now in the crystal structure?
10, sir.
Yeah. Do you require any extra energy?
Okay. No, sir.
That's what I told.
Okay.
The system you need to consider as a whole, as a system. You are only thinking about one electron or one hole like that, but it's not independent. No, as a whole of the system you have to consider.
Okay, sir. Thank you, sir.
Yeah. Please, Sneha sis, please go ahead.
Good afternoon, sir.
Very good afternoon.
Sir, I have doubt of previous classes, sir. Yesterday class.
Yeah.
Sir, you have described the passive and active device. Can we justify it from graph, sir? Because you have written some points, but if they give graph or any, we can do
which graph? Which graph?
Sir, passive.
See, one second, please. I have just defined active and passive, which is required for my subject. Okay. Actually, you need to study that. I think maybe in network theory you are going to study it.
Okay.
So there you can get it. I cannot explain with the graph here.
Okay, sir. Thank you, sir.
Is it okay? Fine.
Okay, sir.
Kalyani, please.
Good afternoon, sir.
Very good afternoon.
Sir, you have told that for the generation of the free electron, the temperature should be at the room temperature, sir.
Not at room temperature. It should be greater than.
Passive device
Yeah. Those who got clarified, please unmute your voice. I'm getting some other voice also. Please. Yeah, please, Kalyani, go ahead. It's not room temperature. Simply T greater than 0 Kelvin. Okay, you can break the covalent bond.
For the even for the hole and for the generation of hole and for free electron, the T should be greater than the absolute 0.
See how you are getting hole. If you break a covalent bond, that's what, if you remember very clearly, I have mentioned many times, electron hole pair.
Yes, sir.
If electron is there, corresponding to that, free electron is there, corresponding to that, there is a hole.
Okay. So T should be greater than absolute 0.
Obviously, because T equal to 0 Kelvin, how there is no energy at all, no, for your.
Okay, sir.
Fine.
Thank you, sir. Yes,
Yeah.
sir.
Vidya, please. Vidya. Jivika.
Hello.
Yeah, please.
Sir, is it always true that effective mass of
Please, your voice, there is no clarity, lot of disturbance I'm getting.
Sir, is it always true that effective mass of electron is less than the effective mass of hole?
Effective mass of electron is?
Always less than the effective mass of hole in all the material.
No, it depends on what type of material, what type of parameter you are. Whatever I've given here is with respect to the conductivity. Conductivity effective mass of electron is less than conductivity effective mass of hole. Parameter, it is not a absolute term, it is a relative term. Effective mass is a relative term.
Okay, sir. Means here we discuss in terms of conductivity, but when we discuss in terms of different material, then it will be different.
No, obviously, if parameter changes, it may or may not be.
Okay, okay, thank you.
Yeah. Rohan, please go ahead. Yeah, another 5 minutes, please. Make it fast.
Am I audible, sir?
Hello.
Hello.
Yeah, it's very low. Your voice is very low.
Hello. So what is the need of having effective mass if we already have actual mass?
Huh? What is the
Need of having effective mass.
See, it is not the need, man. Actual mass, where you are defining? Actual mass in which medium you are defining? Hello.
In air medium.
Air or vacuum? Yes or no? But are you working in vacuum now?
No.
Then you should have effective mass. Clear?
Yes. Thank you, sir.
Yeah. Yeah, Jnana Meghna. Ram, please go ahead. Shreya.
I'm audible, sir.
No.
Am I audible?
No. There is a lot of disturbance. Your voice is very, very, low. Vidya? Krishna?
Hello, sir. Can you hear me?
Yes. Who is
Sir,
this?
sir, is the characteristic? I mean, is characteristic of electric dipole similar to that of photon, but electric dipole is not a photon. Is it true, sir?
Come again.
The characteristics of oscillating electric dipole is photon is similar to that of photon, but photon is not electric dipole, right?
Why you are saying that statement? I am not getting.
Sir, because you gave that corresponding particle nature is photon, no, sir.
Obviously.
So I thought that oscillating electric dipole corresponds to photon.
No. See, please try to understand. You are mixing so many things, man. Why? Whatever the statement that you are giving, is it really matters? Please think. You are creating confusion for yourself itself. What I explained is when there is an electric dipole which is oscillating, from that I am getting the electromagnetic wave. What is that electromagnetic wave? It is a form of some energy. Now energy can propagate in the form of traveling wave as well as the particle. So for that electromagnetic wave, what is the corresponding particle nature? Photon I am calling. But you are not supposed to reverse engineering. If you do, and you may not, you are not supposed to conclude in that way.
Oh, okay, sir. I got it, sir. Thank you, sir. Thank you very much.
Yes, yes. Vaishnavi?
Hello, sir. Hello,
Yeah.
sir. Good afternoon.
Very good afternoon.
Sir, in the page 19, in the same page, sir, I just need to confirm one thing.
Yeah.
If you break a covalent bond, an electron hole pair is generated.
Fine.
Means an electron is made free and a vacancy is created,
Fine.
which is represented as a positive charge.
Fine.
So the 4 near neighborhood electrons are known to be bounded, which tend to occupy.
Not only 4 neighbor, there are many.
Okay, so that's what I didn't understand. What exactly is a bound electron, sir? The nearest neighborhood or?
No, not nearest neighborhood. All, if you see here in the representation which are given,
Yes,
except this broken, all other are going to be what? Bound electrons only, no?
Okay, so but the nearest neighborhood are more tend to occupy.
Yeah, obviously, no. Nearby, they have more, possibility or probability that they can occupy.
Okay.
It
So if
may not
they-
be necessary. It may not be necessary, but most of the times it will happen.
So if they occupy that hole will be moved into
Moving in the opposite direction to where
which-
come it is. Yeah.
So the creates the mobility of positive charge.
Obviously.
Okay, so page 21.
21. Yeah.
So here you discussed about the speeds of electron and bound electrons. So speed of free electron is greater than bound electron. What about speed of holes are here?
Bound hole. Where from you are getting hole?
That's what, sir. If bound electron is moving, hole will be shifted.
Yeah, the same. No, bound electron is and hole moment, they are in opposite.
Okay. No, it's speed. I'm talking about the speed. Will it be equal to bound electron speed?
Yeah, obviously.
Okay. Yeah. Okay. Yes. Okay. Thank you.
Yeah. Tejasri.
Good afternoon, sir.
Very good afternoon.
Sir, I'm confused regarding phonons and photons.
Mhm.
Sir, in any atom, when vibration occurs, there would be obviously there would be change in the center position, effective center, no, sir. So then photons and phonons will occur compulsory for every vibrating atom, sir. Is that
Fine.
true?
Yeah, it can be. But what you are going to do with that is important. If it is not significant, okay, but why I'm considering here for semiconductor, these things are required for us. No, you need to understand how the free electron is generated, hole is generated. No.
Yes.
Okay, for that purpose, I have started with the vibrating atom, which is the phonon. Then from that we are getting photon. Now, if these are interfering at a particular point, then what will happen? There is if that energy is equal to the energy gap, sorry, not energy gap, bond strength, then it will be broken, and from that you are getting free electron and hole. Are you getting my point?
Yes, sir.
Yeah, it can happen in whenever there is a vibrating atom, it can happen, but out of which what you are going to get is the important matter.
It can happen or it will always happen.
No, it can, because we are confined to only particular point, and we are not supposed to conclude. There are many other factors also, no? Because semiconductor, you consider some other material, it may.
Okay.
Same.
Yes.
So there are many factors which you have to consider. Getting?
Yes.
Yeah, Shreya, please. I think there is a problem with your voice. I'm not getting.
Am I audible, sir?
Yeah, now it's fine. Go ahead.
Am I audible?
Yes. Go ahead.
Sir, in page number
Page number? Hello?
8F.
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 1 second. Yeah. Fine. Please. Hello? Shreya.
So here you told that no net transfer of energy should take place. With respect to what, sir? With respect to environment?
With respect to?
Sir, in order to transfer an energy, there should be two bodies, no, sir. One will refer to semiconductor.
Within the same body, there is no transfer of energy. Within the same body, energy transfer will not happen.
Will happen, sir.
Then why you are saying to have energy transfer, two bodies are required? Okay. Anyhow,
Okay,
come to your doubt first. Come to your doubt.
Sir, here second case.
No.
We have
previously,
applied.
Previously, you have one doubt. No, you have not clarified. You are going for second.
There is no net transfer of energy or charge.
Fine.
What you are saying, do not have any transfer of energy.
What is the transfer of?
With respect to what you are saying, that there should not be any transfer.
What you
of
want? With
energy.
respect to what you want, I'm asking you.
Is it with respect to environment or is it with respect to anything or itself?
1 second. What is the definition that are given for the equilibrium? Please check it. Please check the definition in the previous page, 7F. What it
environment?
Is between semiconductor and environment as well as within the semiconductor. I said no. Then
okay,
what? Then what? With respect to what I am talking now?
With respect to environment or
as
with
well as
respect
within
to
the semiconductor. That's what
So
I am telling you.
second-
You need to understand the definitions very carefully. Once you get that, these things will become easy. Okay, go ahead with the second.
In same page, in second case, when you apply illumination, that is light, there will be a free generation of electron and hole pair, sir. Due to the disturbance of concentration, the second case is wrong, sir.
Obviously, that is what I said. Second condition, there is no net transfer of energy, but here there is a transfer of energy or charge. No, that is why it is not satisfied.
At one point to another point, only in semiconductor, the energy is transferring in semiconductor from one point to another point. That's why we told that it's wrong.
No, here not energy. It is a charge. No, charge is moving from higher concentration to lower concentration. Second condition is not satisfied. No, for that.
Because of that reason only I am asking.
That is only. I said very clearly.
Okay, sir. And if we break a covalent bond by applying.
Please 1 second. Your voice, there is lot of disturbance. No, it's not very clearly. I'm getting very
I'm audible, sir.
No.
Now
Pass.
I'm
I'm getting pass and pass and pass.
Now I'm audible.
No. Initially it's okay, but again it's pass.
Now I'm audible, sir.
Yeah, fine. Go ahead. Please make it
Sir,
fast.
if we give some energy to a crystal, there will be we can have a covalent bond broken, and we will get a free electron.
Fine.
And a hole. Sir, we said that the energy need for bond electron to get into the vacant place is less. Because of that, because electron have the negative charge and vacant place have the positive charge, so they get attracted to each other. That's why we said that less energy is needed, sir.
Maybe you can understand in that way, but that is the not actual reason. See, whenever you see this, where it is. See, when there is a vacancy here, okay, always these bound electrons will try to occupy. No, obviously.
Yes,
it's not in and that is what. So there is already there is a tendency, and there is no need to apply any external energy.
Is the tendency due to the attraction between the bond electron and the vacant place called hole?
No, that's what I'm telling you. See, once we have position and bound electron, from that you are defining what is hole, not in the reverse direction. Okay. After that, we got bound electron and hole are moving in the opposite direction. Okay. Bound electron is negative, so hole is positive.
Due to the tendency, we call that hole as a positive charge, right?
That's what I'm telling, man. Free bound electron and hole, they are moving in the opposite direction. Yes, that is the reason why we are giving hole positive charge. But in reverse way, that statement may not be correct what you are telling. There are many other things that you need to consider in the crystal structure. Okay.
Okay, sir. And the doubt, sir. You said that movement of electron is much faster than movement of bond electron. How you told that? I didn't get it, sir.
You are not able to understand it.
Yeah.
Okay.
How you justified that?
Yeah, I'll justify. See, suppose I hold you and ask you to run. Okay.
Yes, sir.
How fast you can run? I am releasing you and you are running. How fast you can run? Which one is faster? Which one is faster?
Sir, can you please repeat it again?
I am holding you and ask you to run.
Okay, sir.
Okay.
Okay, due to that bond.
Second case, I am releasing you. I am not holding you. I ask you to run. In which case you can run faster?
By releasing, I can run faster.
That is what here also happening, no?
Okay, okay. Thank you, sir.
Fine. Okay, so we'll meet tomorrow sharp 9 o'clock. Please, students, at least you come 10 minutes before. Okay, thank you.